Welcome everybody to the session on Linux Binary Exploitation. So this is the plan for today. We will begin by discussing some simple buffer overflow on 64-bit architecture. We will begin by disabling all exploit mitigation protections like NX, Stack Canary, ASLR, PIE and all that. If you are hearing these terms for the first time, there is no problem. I will explain all of these, what NX is, how it prevents buffer overflows, and what canaries are, how they prevent buffer overflows, what ASLR is and what PIE is and all that. So once we are done with a simple stack-based buffer overflow, we will get into return to libc and return-oriented programming. So that's to bypass NX or non-executable stack. And once that is done, we are going to see another technique called return to PLT, which is going to bypass both NX as well as ASLR, but we will still have to disable PIE, position independent executable, for this particular case. And once that is done, we are going to get into format string vulnerabilities. You might have probably read about format string vulnerabilities in general on different blogs or in videos and all that. But in this particular training, specifically, we are going to make use of format string vulnerabilities to bypass some restrictions like NX, ASLR and all that, and exploit buffer overflow. So essentially what that means to us is we are going to chain format string vulnerabilities and buffer overflow vulnerabilities together, and we are going to write some exploits. So specifically, we are going to use format string vulnerabilities to bypass stack canaries. That's one exercise. And once that is done, we are going to enable all the protections. I mean, we just compile the program just like a standard developer. We won't be using any additional flags to disable any protections. And then we will write an exploit from scratch. So that's going to be the end of the training. Now, obviously, as you can already sense, it's going to be very, very complex, and it's going to be too long. I really want to cover all of these topics within 4 hours, but obviously you will have to pay a lot of attention as well, because if you miss something, I think it will just go above your head. Now, this is the plan in terms of the time. We will try to take a break about like after 2 hours, and before the break, there could be only one break. If you want, we can take some short breaks, like 10-minute breaks in between as well. But the original plan is to have one break after completing simple buffer overflows, return to libc and return-oriented programming, and return to PLT. Once these concepts are completed, we will take a short break, like 15 to 20 minutes. And after that, we will begin with format string vulnerabilities and leaking memory addresses, and then some other things like chaining format string vulnerabilities and buffer overflows. So that's the plan. I think we can get started. So before we get into writing simple buffer overflow exploits, I have about 2 slides to cover the registers, because if you are from 32-bit background, you may have probably seen these registers here, like EAX, EBX, ECX, EDX. They are, as you can see, they are 32-bit registers. Now in 64-bit processors, we have more registers than what you might have seen in 32-bit registers. RAX, RBX, RCX, RDX, RSI, RDI, RBP, and RSP. These are the general purpose registers that you can easily compare with the 32-bit registers that you might have already seen. But in 64-bit, there are few more additional registers that you can use. Here they are. These registers were not available in 32-bit processors. So R8 to R15 are the new registers that were introduced in 64-bit Intel processors, right? So if you go back to the previous slide, if you take RAX register, it can hold 64 bits of data, and you can still access the 32-bit register using EAX. And within EAX, just like your 32-bit processor, you can further access the 16 bits using the AX register, and you can also use these 8-bit registers as well, like AH and AL. Now, There are few registers where you can't access these higher 8 bits. If you see this RSI, you can't access that. Similarly, RDI, RBP, and RSP. Now, if you are from 32-bit background, you might have probably, if you have written some simple buffer overflow exploits, you might have probably seen Eip Register and Esp Register. Eip is the extended instruction pointer, which is always going to point to the next instruction to be executed. In 64-bit processors, that register is Rip. So we always want to get control on Rip register whenever we write exploits. Now, the stack pointer here is RSP. So typically when we write exploits, these are the two registers we are going to deal with. Remember, we also need this Rbp register, the base pointer, which is going to act as a trampoline, because there are few reasons you need to know about this Rbp register as well. You don't need to know a lot of details about Rbp register at this point of time, but when we try to get control on this Rip register in 64-bit exploit development, we will usually get control on Rbp first, and then we will try to achieve control on Rip. It kind of doesn't make sense at this point of time, but when we write buffer overflow exploits, you will understand this. Yeah, apart from that, I think that's all you probably need to know before we write 64-bit exploits, buffer overflow exploits. Yeah, so as and when we come across any new topics that are not covered in 32-bit exploit development, I will try to cover them, but otherwise I think we can get started with exploit development concepts. I don't want to spend time on how to write simple assembly programs and all that. So I would like to simply get into the stack-based buffer overflow exploits. So this is the VM that you all have. I hope you have it. Guys, can you please say yes if you are able to see my VM? All right. Okay, cool. Do you also have the VM with you now? Okay. Okay, so if you see the current working directory, after getting a terminal, you should see something like this. I have changed all the settings for you to have better font size and all that. So you may not have all these files. I think I have just deleted all of them when I was giving this VM to you, but this is my original copy of the VM. So within this we have a directory called backup, and within this you will have all these binaries and exploits that we are going to use today. So obviously if I'm just using the same directory, I will be just running the exploits and I'll be just showing them to you. Rather, I will go with a new directory and I will recreate everything there. So let's call it x64 training, and let me also navigate to this simple buffer overflow, and let's just copy the vulnerable program from here. Okay, so this is going to be my current working directory throughout this simple buffer overflow demo. Now, if you have already completed the challenge that we have given before the training, the pre-training challenge, this particular exploit is going to be the same, but for 64-bit architecture. Surely there are some differences that you will notice shortly, but the concept is same. I think it's the same vulnerable binary that I have given to you, if you notice this. But we are going to recreate the exploit on a 64-bit machine. Now this is the vulnerable C program. Now we also have a make file. I'll just copy that. You don't have to do all of this. I think it's going to take a lot of time if you do this. So I'm just going to do this for you, and you can just concentrate on the demos. Okay, so if you notice the make file, we are disabling the stack canary by using this flag fNoStackProtector, and we are also disabling the NX bit by using -z execstack. And I think you can ignore this for now because we're not going to deal with that. Now, if you want to compile this program, we can just type make. And if you type ls, you should see a new binary here. And this is the binary we are going to deal with. Now, there is an additional step that we have to do before we get started with writing this exploit. So if you noticed, we have disabled execstack, which is stack. That means the stack becomes executable. And then, we have enabled execstack flag, which means the stack becomes executable. And there is one more protection here, which is stack canary. We have disabled that. So we have disabled two protections so far, and we are also going to disable ASLR. For ASLR, I have, instead of disabling ASLR manually every time, I have written some helper scripts. So what we are going to do is we will navigate to ASLR directory here, and here you can actually run these scripts to verify or disable or enable ASLR. To get started, let's verify ASLR. If the value is 2, it's enabled. So let's disable it. Let's verify it once again, and there you go. You can actually take a look at the contents of these files to see what's actually being done inside. We are just writing the value into this particular file. Okay, so we have also disabled ASLR. Right, so we have disabled all the exploit mitigation protections, NX, stack canary, and ASLR. We will enable them one by one later, but for now, I think we should just get started with this. Now, just like how we have done earlier in the 32-bit challenge, we are going to crash this program by using some large buffer, and then we are going to try to identify the offset that is required to overwrite Rbp register, because Rbp is something like Eip in 32-bit. Okay, so once again, I will just copy the template from here. Instead of writing that, I'll just copy the template and I'll build on that. Okay, so this is the template that we are going to use here. Okay, I think I'll also disable the PIE, which is by using the flag -no PIE. You have to bear with me for now. With all these flags. Later in the last demo of the training, we are just going to compile the program using this particular command. So that means we are not going to use any of these flags later. For now, to understand the concepts better, I think we should disable them. Now let's start crashing the application. If you notice, the vulnerable binary has an strcpy function, which is taking input, and this input is actually coming from here, and this is the argument to the program. So what that means is we can execute the program like this, and this is going to be the buffer that is going to crash the program. So instead of manually typing these A's, we are just going to use this Perl script. There is a reason why I'm using Perl here, because earlier I was using Python for most of my templates and exploit scripts. But when they switched to Python 3, I think some of the concepts were, I was not so comfortable with Python 3, and some of the concepts were not so clear. So my exploits were requiring some modifications. So I thought it's a good idea to move to Python 3, move to Perl. But later I had to use something called pawn tools, which we are going to discuss today at the end of the session. And when I was using pawn tools, I still have to use Python 3. So it was not leaving me. So today, most of the exploits that we are writing are going to be in Perl, but at the end of the session, we are going to use Python 3 when we specifically use pawn tools. Okay, so as you can see, this is a simple Perl script. This is the shebang, and we have this line. This is just to, I think this is just to process the buffer, something like that. Let me just explain that. I'll get back to that. I think that forces a flush after every write or print. So that's the reason we are using this. I think it just saves some time. And we are using a variable called junk, which is having 300 A's. So if you notice the buffer that we have here in the vulnerable program, it's just 256 characters. So we are just trying to write 300 A's. So it's going to cause a crash. So there is, let's produce the payload using this exploit 1.pl. Let me just change the permissions. I'm assuming that you're understanding whatever I'm discussing here, but if you don't understand why I'm doing a specific step, I think you can stop me and you can ask me in the chat. Feel free to post your questions in the chat if you don't understand a specific step that I'm doing here. Okay, so we have made it executable, and let's produce a file called payload1. So all the 300 A's should be available in this file. You can quickly check that by using a hex editor, xxt space payload1. And if you see, all the 300 A's are available here. Okay, now let's try vulnerable cat payload1. So basically we are just passing those 300 A's to this vulnerable program as its first argument. As you have seen, this is going to be copied using strcpy function into a buffer of 256 bytes. So this is going to cause a crash. Let's hit enter. Look at that, there is a segmentation fault. Now if you type ls, even though there is a segmentation fault, there are no core files generated in the current directory. So you can do ulimit -c unlimited. And if you try to cause the crash once again, and if you check the available files in the current directory, there should be a core file. So core file is something like your black box. When there is a flight crash, you want to know what happened at the time of the crash. So typically people go and look for these black box, right? So similarly, if you have the core file, you can understand what happened at the time of the crash. So I'm going to use gdb -core. We are going to debug the actual binary in a moment, but let me just quickly show you how to use the core file. -core and the actual name of the file, which is core, and hit enter. And if you notice, if you have never seen this Jeff shell, and if you're seeing it for the first time, Jeff is a plugin for GDB. It is going to make our life very, very easy. I'm not going to use plain GDB. I'm going to use Jeff for almost, not almost, I think pretty much everything in this training. So we are going to use Jeff. Jeff, I think it stands for GDB Enhanced Framework or something like that. You can search for it online. Now, a lot of commands that you typically type within GDB can be, without typing them, you can basically see those outputs using Jeff. For instance, if you want to see the stack, if you want to examine the stack, you can just run the binary and you will be able to see the stack on the screen. It's like UI. You will have a lot of details in front of you if you are using Jeff. So as you continue with the training, you will understand how and why I use Jeff. Okay, so if you notice, there seems to be a crash here at this address. So when this address was triggered, the application was unable to understand where to go and the crash happened. Typically, if you are on a 32-bit machine, you would be seeing 41, 41, 41, 41, which are the A's that have caused the crash, right? But this is what happens on a 64-bit machine. You won't be seeing that by default. So I'll explain in a moment why that is. Now, let's try to examine the registers. We can use info registers to do that. There is a typo there. Okay, look at that. If you notice, Rbp register is containing this value, which is what exactly we have seen here, which is causing the crash. But if you see this Rbp register, it has our 41, 41, 41, which is some text from the 300 A's. So this is what is, this is a confirmation that our buffer has caused the crash, but this is still unclear why Rbp doesn't contain these 41s or A's, right? We will solve that mystery in a moment, but for now, our buffer of 300 A's has caused the crash. All right, so basically this is what you can do with the core file. You can do much more than this, obviously, but I won't be using the core file, but I just wanted to give you a basic introduction to core files. So let me just quit here and let's directly run the binary using GDB. I'm using gdb./vulnerable, that's the binary, -q, so that it'll run in quiet mode. It doesn't show a lot of information on the screen for me. And yep, I think that's pretty much it. There it is. Now the binary is loaded using GDB. Now, if you see this binary, the vulnerable program, it has a main function and within which we have all the other code. So typically when we debug using GDB, we want to set up a breakpoint at main and we can proceed from there. Now, if you notice, this program requires, as you have seen earlier, this program requires an argument, which is going to be the large payload that we are supplying. So when you run this program using GDB, you can actually pass the payload like this. So the payload 1 is from your local system, which is containing the 300 A's, and we are just passing this as an argument to the binary and we are just running it using GDB. So let's hit enter. And let's quickly examine the registers once again. So far nothing happened because there is a breakpoint at main. It hasn't executed the strcpy function yet. But the idea here is to see the UI or the output of Jeff shell, output of Jeff. If you notice, currently we are seeing registers. If you are just using plain GDB, I think every time you want to see the registers, you will have to run these commands. Otherwise, you will have to do some sort of basic GDB scripting. Now, if I'm using Jeff, you can basically see the registers every time. And you can also see the flags. If you see this, these are the flags. So you can see which flag is set and which flag is not. And you can see the stack here. This is the stack. And these are the instructions being executed in the binary. If you see, we are currently at main +0 and Rbp should be pointing to this address. Let's check that. Here it is. The Rbp register is pointing to the address ending with 5149, address ending with 5149. So that's basically Jeff. We are going to use Jeff a lot, and I think it'll be clear by the time we end this training. Now, let's disassemble main by using the command disas main, and we can see there is a strcpy function. I think there is a vuln function within which we have strcpy. So we can probably run disassemble vuln function, and this is what is going to be causing the buffer overflow, right? So once this buffer overflow happens, what happens is this return address is going to be overwritten. I mean, so once the strcpy function is called, it is going to it is going to cause the buffer overflow, and this vuln function has to return to the main function. But because of the buffer overflow, this return address will be overwritten and you will get control on the Rbp register. So that's what is the buffer overflow here. Now what I'll do is I'll probably set up a breakpoint here at the ret instruction by using b space the address. Notice the star here, and let's continue with the execution and see what happens. I'm typing C to continue with the execution, just in case if you didn't notice. So if you notice, the stack has now our buffer. The buffer is placed on the stack, and if you see, there are a few registers which are holding the value of these A's: R9, RBP, RCX. And RIP still doesn't contain what we are expecting. If you want to know the offset to RIP, obviously you should be able to overwrite the Rbp register, right? So, but unfortunately we are unable to overwrite Rbp register. So any idea how we can get there? How do we get the offset to Rbp register? You can post your answers in the chat. So the question is, we have supplied 300 A's. Clearly we are able to overwrite Rbp register, but we don't have control on Ip register. And if you don't have control on Ip register, obviously you can't exploit the buffer overflow. Sachin Grover says increase the number of A's. Actually, Sachin, it's not needed because we have already enough A's, but I can do that. I can show you, but we already have enough A's. We are already overwriting Rbp register here. But let me show you, since you asked for it. Let's copy exploit one to which memory location? The RIP. I mean, your idea of exploiting the buffer overflow is correct, but currently we don't have control on RIP. To jump to a specific address, first you have to be on the RIP register. You need to have control on RIP register. So currently, if you notice, if you remember what I was showing you earlier, our A's are overwriting Rbp register, but our A's are not overwriting Ip register. So to come to the point of what you are explaining, I think we first need to overwrite Ip register, but we don't have that control. So you're saying 300 A's are not enough. Probably we can increase the number of A's. So this is the first problem with 64-bit exploitation. Okay, so let's probably make it 350. Will that be sufficient? Do you think? I think it's 300 is good enough, but just to follow what you're trying to say, I'm just increasing this to 350. Payload 2 and GDB. The reason why I am also asking you not to do all these things, because I'm going to do it multiple times. For example, if you currently don't know how to load a binary, probably you will see it 100 times today. So by the time you finish the training, you will know how to load the binary, how to set up breakpoints and all that. So let's once again go to disas vuln function, because we want to have a breakpoint at the ret address, which is this. There is a small typo in the make file. I'll fix that later, but for now I think we can set up a breakpoint at main first, and let's run the binary using the the payload 2, which is having 350 A's, and run the binary. We are done. Then let's set up a breakpoint at the ret address, which is this. And if you want to execute system commands from the GDB shell, you can use the shebang or shell. So for instance, if you want to clear the screen, shell space clear, that will clear the screen. Or you can also use like this, the exclamation mark and clear. This will also execute system commands. Okay, now let's continue with the execution, and we should have 350 A's, and you still have control on Rbp register, but there is no control on Eip register. Any other guesses or any other ideas how we can why or how? Anything is fine, just your thoughts or ideas. Doesn't need to be correct, I don't mind, that's why we are here. It's it's very hard to teach to my screen if you're not responding. Okay, okay, so that's limitation of 64-bit processors. There is a reason which I'll explain now. Let's type VM map. It shows you it shows the virtual memory map of this process. You can see vulnerable, and you have libc loaded here. Once again, don't get confused or don't worry if you don't understand these outputs and all that. We are going to deal with all these things multiple times, so you will understand them. And this is the dynamic linker, and we have stack here. Now, if you notice the starting addresses of all these entries in the memory map, except for the last one, which is associated with the kernel, all of them are having only 48 bits out of 64 bits. The remaining higher 64 minus 48. Let me. So if you see this, there are first 4 zeros in every address here. In almost all the addresses, not almost. It's in all the addresses. We have 4 zeros at the higher addresses, and only the rest of the 48 bits are used. So this is 64-bit processors. So basically, in 64-bit processors, the memory addresses are like this. Let me go back to my slides. So they call it canonical address. They call it canonical addressing, and what it means is, when you're addressing a memory, you can use only these addresses. If you notice, starting from this address until this address. But when we are trying to overwrite RIP, we are basically using 41 here, and 6 more 41. So basically we are using 8 41s. That's the reason why we are it's not able to show what RIP contains. So what it actually means is, you cannot have 8 bytes of addresses. I mean, you cannot have all the 64 bits on the addressing. So when you're addressing a memory address, you only can have these lower 48 bits. You can't have 8 A's. You can only have 6 A's. So that's what it means. So the non-canonical addresses, I think, are only used by kernel, but for the user space, this is the address range we can use, and that's the reason why the memory map shows only these addresses. So if you go back, give me a moment, please. So yeah, here we are. So basically what that means is we cannot overwrite Rbp register with 8 bytes. We can only use 6 bytes, and that should give us the control, because we need to use proper memory addresses. That's what I mean. So let's try updating the exploit to with something with some buffer that overwrites only 6 bytes of RIP. But even for that, we need to know the offset, right? So if you want to overwrite only 6 A's into the RIP register, you need to know exactly how many bytes of junk is required to reach the RIP register. For that, we can use Rbp register as our intermediate register, and so that basically we will find out the offset to Rbp register, and from there we can add 6 bytes to reach Ip register. So what that means is, let's try to once again load GDB vulnerable, and let's set up a breakpoint at main, and let's run the program. Before running this, let's probably use some offset this time, because I assume all of you know pattern offset, pattern create and all that. So I'm just going to use some random pattern instead of using 300 A's this time. So for that, what we can do is we can use instead of using metasploit, that's what we are habituated to do when we learn buffer overflows in OSCP and all that. In Jeff, you have this feature called pattern create. We can use pattern create to create a pattern of 300 bytes. So we have I'm just copying this, and let's go back to x86 training. Okay, let's update the exploit 2.pl. So instead of 350 A's, we are just going to pass the pattern that we have just produced. Okay, so that's the pattern. Let's save. Yep. Yeah. You mean this pattern? We don't know yet. If there is any bad character, usually it won't be copied. Typically, it won't contain bad characters, I guess. But to answer your question, if it contains any bad characters, obviously the full buffer won't be copied through the payload. Yeah. So let's assume that it doesn't contain any bad characters. In this case, it doesn't contain any bad characters because for strcpy, null bytes are the bad characters. So the moment it encounters null bytes, the payload will be terminated there. Typically, it depends on the vulnerable program. For instance, in our case, the vulnerable program is using strcpy, so null byte is one of the bad character. Similarly, if it has more checks for the incoming data, probably that becomes a bad character. If you take gets vulnerable function as an example, 00 or null byte is not a bad character for gets. It can still take the input even if you have a null byte. But if your input has new line character, the exploit will terminate there, because gets will stop reading the input the moment it encounters a new line. So depending on the vulnerable program, you will have to find out the bad characters by passing all the hex values onto the target vulnerable program. I think in this particular training we have very less amount of time to cover how to identify the bad characters. the assumption is that you know how to identify the bad characters. Anyway, we are not going to deal with too many bad characters in this training. We are for us it's only null byte in this particular program. In the I'll move on to another binary later. In that, only a new line character is a vulnerable, bad character. Yeah, so to answer your question directly, this buffer doesn't have any bad characters. So yeah, so let's produce the payload exploit2.pl and let's call it payload2 once again. Now let's run the binary using the new payload. So this payload contains this particular pattern that we have just produced. We ran the program. Now let's once again go to _function and let's set up a breakpoint at the ret address. Okay, so once that is done, we can continue with the execution. You can either type continue or you can just type C. So if you notice, we have continued with the execution and we are about to execute the ret instruction under _func. Now, if you notice the Rbp register, it's overwritten with some pattern, but still Eip register is not overwritten because after Rbp you can only pass 6 characters. You can't pass 8 characters because that's an invalid address in 64-bit. Because that's what I was trying to explain. If you see this, the first 4 characters are zeros, right? So the first 2 bytes are zeros here. You can't have 41s there. Now you need to find out the offset to this Rbp address because Eip gets overwritten immediately after Rbp. So if we know the offset to Rbp, we can actually calculate manually to Eip. Now let's go back to the previous terminal once again, or let's probably use clear pattern search. This is the command to find out the offset. So I'm just searching for this particular pattern, and if you notice, 256 is the offset to overwrite Rbp. Now let's update the exploit. So the moment we update the exploit, you will get a picture of what we are trying to do here. So let's just open exploit3.pl and let's remove this variable junk and let's give it 256 A's, which is sorry, it should be A here, and since I am talking and typing, I am making some weird mistakes. Please excuse me for that. Okay, so we have 256. This is the offset to Rbp register, and we have next we have Rbp register. Remember, the 6 bytes condition is applicable only for memory addresses. Rbp is just a register. We are not using it as a memory address, so we can still use 8 bytes here. So I'm just using 8 bits. And next is what is going to be our Ip register. If you remember, Ip register has to be, it cannot be 8 bits. It cannot be 8 bytes. It can only be 6 bytes. So we are going to use 6 Cs, and that should give us control on Ip with these 6 Cs. So 256 is the offset to reach Rbp register. So using these 8 bits, we are overwriting Rbp register, and after that, these 6 Cs should contain, should be used to overwrite Ip register. So let's copy, let's save this file, and let's produce exploit3.pl, and let's save it as payload3. We are producing the payload from exploit3.pl, and we are saving it as payload3. And let's probably run this once again using payload3. So whatever the breakpoints that you have set earlier will still be relevant. We are just rerunning the program using a different payload. So we don't have to load the binary once again. I'm just hitting enter. And if you notice, this time we are still at the main. So let's continue with the execution. to see if we got control on Rbp register. Look at that. We have Rbp, the 6 C's on the top of the stack, and the next instruction to be executed is ret. When you execute ret instruction, behind the scenes, pop Rbp will be executed. What that means is the value on the top of the stack will be popped into Rbp. So currently, if you see, we have 8 B's in Rbp that is expected, and 6 C's on the top of the stack that is also expected. So if you do a single step, we should have these 6 C's in Rbp register. Let's check that. So I'm just typing SI, which is a single step to execute one instruction. So that is going to execute this ret instruction. So I'm hitting enter. There it is. If you notice, we now have control on Rbp register. Is that clear? So the reason why we are doing this way is in 64-bit architecture, the usable address space is limited, which is called as canonical address space. Now, attempting to use non-canonical addresses will cause a segmentation fault because they are only used by the kernel. And we have been noticing segmentation faults earlier because of the fact that we were overwriting Rbp with a non-canonical address, right? And yeah, that's pretty much it. So we managed to use a canonical address, an address which is in canonical address range, and we managed to overwrite Rbp register. If this is clear, I think we can now we now have control on Rbp. Now all we have to do is we will just have to place some shell code in the buffer and then redirect the execution just like your 32-bit exploit. Let's do that. I'm just quitting it here, and let's save exploit3.pl as exploit4.pl. The numbers that I am using here, like exploit1, exploit2, could be different in your VM, in the exploits that I have earlier written, because I'm not checking the file names of the older exploits. I'm just rewriting them here. So what's wrong here? Okay, so let's move exploit4.pl to exploit4.pl. There is a typo there. Okay, and let's use this exploit4.pl to place some shellcode in the beginning, and we can also redirect the address of this. We can override this 6 C's with the address of the shellcode. So that's the next step. I'm just going to quickly do that. Try to pay some attention here, how I find out the address of shellcode and how I overwrite the address of the Rbp register and all that. Okay, so let's create a new variable here called shellcode. And we can actually get shellcode from the internet, or we can write our own shellcode. In the VM that I have provided, I have written some custom shellcode. Let me just navigate to the directory. There is a directory called shellcode. There is exit shellcode, there is execve shellcode, and there is a reverse TCP shellcode. We are not going to cover how to write shellcode in this training, but yeah, if you understand how shellcode can be written, I think you can just take a look at these files, and you will have custom shellcode written from scratch. Now, what I'm interested in is the execve shellcode, which is execve2 here. This is the shellcode that I have written, but if you want to use the shellcode from the internet, you can feel free to do that. Now, one thing that we need to do is extract shellcode from object dump. So I'm just going to use a one-liner from the internet to extract the shellcode. So I'm just copying this command here, because it's a binary which is compiled and linked, and we need to extract the actual shellcode from this binary. So I'm just using this one-liner from here, and I'll just use these. As I said, this is in your VM as well. You can basically follow the same steps to extract the shellcode. So I'm just using object dump and some Linux kung fu like cut, do, echo, and all that. I'm hitting enter, and we got the shellcode. We can basically use this shellcode. If you want to use shellcode from the internet, you can feel free to do that, but sometimes they may contain bad characters and it may fail. So it's suggest I have already tested the shellcode that I have written, so I think it's recommended to use this particular shellcode. But wait, actually this shellcode has some bad character here, which is a null byte. Let me check why that is. Okay, I think we can use this one. This doesn't have null byte. Yeah, I think we can use this. Yeah, let's copy this. If it doesn't work, I'll probably use something from the internet just in case, but I'm hoping that it will work. I have tested it earlier, but I can't recall which one is the exact file. All right, so we can now also place some knobsled at the beginning. I'll show you the pictorial representation of the exploit in a moment. Don't worry, you will understand that. So let's use /x90, and we can probably use about 30 knobs. Obviously, we'll have to subtract that length from these A's. So we are going to use 256 minus length of shellcode minus length of knobsled. Okay, so this should produce the payload properly, and we will finally have to replace these 6 C's with the address of this knobsled. Okay, so let's save the file. I hope everything is correct. If you see any, there seems to be a typo here in the length. If you see any mistakes, please let me know, because usually silly mistakes are hard to troubleshoot. Like this. Okay, so hopefully this should work. I'm just producing exploit4.pl. I'm producing payload 4 using the exploit4.pl file, and let's quickly check if it has everything. Okay, so that's the reason why I usually check using this hex editor. If you notice, there is no knobsled and there is no shellcode because we did not print them. So let's use exploit4.pl. If you notice, we have all the variables set in the exploit, but we are not printing them. So we will have to first print the knobsled, and we will have to append the shellcode, and finally junk. Okay, so that should fix the problem. Let's save the file and let's produce the payload once again, and let's use hex editor, and this time hopefully it's all good. Let's clear the screen, and let's use gdb-q.vulnerable. So -q basically doesn't print a lot of information here. That's why I use -q. And let's use breakpoint main, and let's run the binary using payload 4. If you notice, I'm first setting a breakpoint at main, and then I'm running the binary using the payload. After that, I'm setting up a breakpoint at the ret instruction of vuln function. There is a reason for that, because this binary has PIE. You can't directly set up a breakpoint on addresses within the functions before starting the binary. If you want to do that, you need to disable PIE. I'm not sure if it is clear, but follow the process for now. for this particular binary. Just set up a breakpoint at main, run the binary using the payload. After the binary is run, set up a breakpoint at ret instruction of vuln function. Okay, so let's run the binary. Now let's find out the address of ret instruction here. Now set up a breakpoint. The binary is already started. Now we are setting up a breakpoint. Okay, so let's continue with the execution. And if you see, we still have 42, 42, 42 in RBP, and we have these C's to be executed. I mean, these 6 C's to be popped into Rbp. Now let's type SI, and this is what is going to be the condition when we redirect the control onto the shellcode, right? Now we want to find out the address of the shellcode. Let's quickly examine the stack. I'm using x/gx 50gx. Usually in 32-bit exploit development, you probably use x/50x, right? Let me show you what happens if you do that. And RSP is the top of the stack. And if you remember, we placed about 300 A's on the stack. So I want to use RSP minus somewhere around 280 or 290. So if you do this, you are still seeing 32-bit format. So to see it in 64-bit format, we will have to use 50gx. Look at that. You are seeing it in 64-bit format. Now, if you notice, this is where our knob sled is. So we have used 280 here. Let's reduce slightly. Let's probably use 276, 270. Yeah, I think we can use this address, because this particular address is currently pointing to the knob sled. So if you can replace the address of, if you can overwrite RIP with this address, the control will be redirected to this knob sled, followed by the shellcode, and the shellcode gets executed. So there are some questions, I think. Oh, is anybody in the waiting room? Yeah, found him. It's Arun Nair, right? Yep. Okay, I accepted it. All right, so hi, welcome Arun. Okay, so if you see this is where the knob sled is. So we can basically use this address. We can copy this address, and let me open Sublime Text. And can you please go on mute if you're not speaking? I am hearing myself. Yep, thanks. So we can probably leave this terminal here, and let's use exploit 4, and let's save it as exploit5.pl. Actually, it already took 1.5 hours to cover this simple one. I highly suspect that we can cover all the topics, but I'll try my best. Okay, so we will have to replace this junk with this address, right? So let's copy this. And you will have to convert this into Little Endian format. So basically, you will like you do in 32-bit exploit development, you will have to write the address in this format: /12 /x12 /xdd. Basically, you will have to reverse these bytes. Instead, I'm just going to use a Perl function called struct.pack. It's not struct.pack, I'm just going to use pack. I think it's in Python, we'll have to use the struct module. and we will have to use uppercase Q for 64-bit addresses, and we will just pass this address. So this function will automatically convert this address into little Endian format for us. You don't have to do anything. So this is going to be the address of Rbp. Okay, so that should redirect the execution to the shellcode, hopefully. So let's try this. I'm just saving the file exploit5.pl, and I'm just producing the payload and saving it as payload5, and there it is. Let's quickly check payload5. Seems fine. Now let's run the binary outside GDB. Vulnerable cat payload5. Let's hit enter. Looks like there is a segmentation fault. The exploit did not work. Let's remove the core file and let's run it once again, just to make sure that we have a fresh core file. There is no core file produced here. Let's try ulimit-c unlimited. Yep, there is a core file. So now let's examine why the exploit failed. I'm using gdb-core and I'm loading the core file. And if you notice, this address is same as what we have copied earlier. So I'm just copying this address just to compare. Seems like it's a different address, not sure why. Let's check. So I'm just going to use the 50gx rsp minus 276, the same thing that we have used earlier, 270. Yeah, if you notice, the addresses outside GDB are slightly different. The NOP sled earlier was actually here at this address, but outside GDB it's slightly different. So this is the reason why, this is also another reason why core files are very useful. So we can just try to copy this address now, and let's try to update the exploit. Let's use a different address this time. Okay, hopefully it should work. Let's produce the payload. I think instead of pressing the arrow button, I think it's easier to type it. But let's execute it. Look at that. The shell we got a bin-sh shell, and you can execute commands. So that's how we can exploit simple stack-based buffer overflow vulnerabilities in 64-bit systems. Let me just quickly show you some slides. So here we have some junk, and our goal is to overwrite Eip Register. I'm just giving a quick recap with a pictorial representation. And we kept some padding here, and we placed some shellcode in the beginning, and we overwrote the Eip Register with some address that points to the shellcode. But just to give some room for error, we placed some NOP sled in the beginning instead of directly placing the shellcode. And we managed to redirect the execution to this NOP sled, and once the execution lands on the NOP sled, it slowly redirects to shellcode, and the shellcode gets executed. Right, so that's what we have seen so far. There are some more things that we can do. You can actually find out if there are any registers that are pointing to the NOP sled, and so this is that. Let's assume that RAX register is pointing to the NOP sled. You can actually see that RAX register in this case will be pointing to NOP sled. I'll show it in a moment. Yeah. So if RAX register is pointing to your NOP sled, what you can do is, instead of hard coding the address that we have gotten, if you noticed, the address was working, the address was different within GDB and outside GDB, right? To avoid such problems, this technique actually helps. You can find out the address of jump RAX instruction. I think this is pretty popular technique when you learn Windows exploit development. They show you how to do jump RSP. You usually search for jump RSP in mona.py, or I mean the Mona plugin in the Immunity debugger, and you will place the shellcode immediately after EIP. That's, I think, the next slide. If you see this, you usually find out jump RSP in this case, and you just place the jump RSP address here and place the shellcode on the top of the stack, which is immediately after the Rbp address. And then you just point your execution to the shellcode by the moment you use jump RSP address here, it obviously points to the top of the stack where your shellcode is there. So that's the jump RSP technique. But in jump RAX technique, the RAX register must be pointing to your shellcode or the NOP sled. So when you overwrite Ip register, you will place an address that's the address of, you will place an address that is having the instruction jump RAX. So the moment RIP gets executed, it will basically execute jump RAX. So the control will be jumped to this NOP sled. Now, where can you find these addresses like that contains the instructions jump RAX, jump RSP, and all that? If you are from Win32 exploit development background, I think you can find them in DLLs or within the binary, right? Same goes here. You can find these addresses within the binary itself, or you can use libc library here. Libc library gets loaded into almost every binary that you use in Linux. So you can use libc library, so you will find these addresses there. I'm going to show you return-oriented programming shortly, where I'm going to show how you can search for these addresses within libc library. So that's pretty much it with the simple stack-based buffer overflow exploit. If you have any questions, please let me know. Otherwise, I will move on to the next topic where we are going to bypass NX. Can you please show the POC again? Okay, sure. This is a POC. Now the question is, if I use jump RSP technique, will that work? So currently we are having the shellcode in the beginning of a buffer, and we are just redirecting the execution to the beginning of the buffer. Will this technique, if you use jump RSP technique, will that work? So what it means is, if you are using jump RSP technique, you will have to place the shellcode immediately after this Ip register. Any idea? Look at the payload that we have used, payload 5. If you see this, we have NOP sled, and we have shellcode, and we have a bunch of A's, and we have a bunch of B's, and finally we have the address. If you notice, 1, 2, 3, 4, 5, 6 bytes, and then we have 2 null bytes. So the moment you attempt to place a shellcode after this, the shellcode won't be copied onto the stack. That's the reason why I'm placing the shellcode in the beginning. So in this case, if you try to attempt an exploit technique like jump RSP, it's going to fail. Yeah, so Daisy says possible only if there is enough space for the shellcode after the RIP overwrite. Let's assume that there is enough space and we are using strcpy. Yeah, that's right. I think Dharmendra says, I think it's not possible since the RIP address will be overwritten with some junk in that case. Yeah, if you remember, we have that problem, right? We were unable to overwrite more than 6 bytes after RBP. So if you try to place shellcode after that, I think it's going to fail. Now that's where I'm going to stop using this binary. We are just going to cheat here a bit. I want to use a binary that allows us to place shellcode after RIP. I'm not going to show you this simple buffer overflow again, but for the rest of the examples, I will simply replace strcpy with gets function. That's the only difference. The rest, the buffer, the length, everything is going to be the same. In fact, even if you change the binary's function from strcpy to gets, the same exploit is still going to work. So let me just go back here and let's go to simple buffer overflow. So I have jump RX, jump RSP exploits also available here, but I'm not going to discuss them in this training because I think it's not required here because we don't have enough time as well. Okay, if you notice, I just replaced strcpy with gets function. That's the only difference. The rest is basically the same. So I'm just copying this file and I will exit here and I'll create a new directory called gets. Navigate there, vulnerable.c, and let's save this here, and let's copy the make file from the directory above this into the current directory, and let's quickly edit the make file because it has some typo. If you remember, there are 2 dashes here. Let's remove one of them. Hopefully this should work. I'm just using make. Yep, there it is. If you notice, the compiler is actually warning us, hey, the gets function is dangerous and it should not be used. Who cares? So let's clear the screen and let's use this function. Now within this current directory we have vulnerable binary, right? So let's copy the exploit from the directory above this and let's paste it here. That's the exploit that we have just created. Now let's produce. So to exploit gets function, obviously we will have to pass the input to this, right? So gets actually reads the input from std in. So to exploit this, we can't just pass something like this. I mean, the previous command that we have used to pass the input to the strcpy binary is like this. But in this case, we can't do that because gets expects the input from the std in. So I'm just going to use exploit 5 and I'll just cat and I'll pass it to the vulnerable binary. Looks like there is a segmentation fault, but I don't think I will go ahead and find it out. If you are trying the same thing, you can probably find it. Probably there is some address mismatch, but it should work. All right, so yeah, so that's pretty much it for the simple buffer overflow. But for the rest of the training, we are going to use other binaries. I mean the binary with the gets function. All right. I'm just going to move on to the next topic, which is return to libc. So next, the plan is, I think we will have to fix the exploit. Let me just get the exploit from here and let's test it. It's the same exploit. I think the address is different slightly. That's why it's failing, but let's try to fix it. Can you confirm if you're able to hear me? Okay, if you see the exploit that I have just copied, it's pretty much the same. So let's try executing this. Okay, there is a segmentation fault. I think I'll have to fix it. Let's try again. Most likely it's the problem with the address. So I'm just loading it using GDB. I'm just leaving my earphones aside for now. If you have any questions, please put them in the chat. I won't be able to hear what you're saying, so please put them in the chat. It's causing a bit of discomfort here. So I'm just loading the core file using GDB. And let's examine the stack. 50GX, RSP minus 280. Probably let's make it 270. Okay. So let's copy this address and let's quit. And let's use getsexploit.pl and let's simply replace this address with the new address. Most likely this is the problem because all of this is tested earlier. Okay, so let's execute it. Hopefully it gets a shell. Yeah, there it is. So most of the times, if the exploits given to you are not working as expected, the reason is either ASLR is disabled when it is supposed to be disabled, or your addresses are slightly changed because you rebooted the system or something happened. You will have to use the core file to actually understand why the exploit is failing. Okay, so that's pretty much it. Now we have a working exploit for gets function as well. So we will be using this gets exploit from here to build our other exploits. Let me just remove the one that was not working. Okay. Now let's go back. And let's create a new directory called NX. And let's navigate there. So we are now going to deal with NX. I'll explain what NX is and how it stops us from executing the shell code and all that. So let's first copy the binary from here. I hope you understood why I'm using gets function. The only reason is we can't place things beyond the Rbp value because null byte will terminate the entire payload after the Rbp register. So we are using gets function so we can place the stuff even after overwriting Rbp register. So gets exploit, and I think we can probably copy everything into the current directory because we need all of them. So let's just put a star here. All right, and let's remove the core file. We don't need it. And there it is. Now let me quickly explain what NX is. First, let's load the binary using GDB. And let's type checksec. If you notice, the checksec utility currently shows that Canary is not enabled, NX is not enabled, PIE is not enabled, and 45 is not enabled, and railrow is partial, the relocation read-only. I'm not going to discuss all of these, but the first three options are going to be bypassed by the end of the training, if we can cover everything, hopefully. Okay, so let me just, sorry, I forgot to show something else, so I just exited. Let me just reload that. Checksec. So it shows NX is not enabled. What that means to us is if you run VM map command, which is part of Jeff, it will show you it will actually show you the memory map of the process. Obviously the process is currently not running, so let's put a breakpoint at main and let's run the program, and let's run VM map once. I'm clearing the screen, and let's type VM map, and if you see, there is an entry for stack as well, and the stack currently has the flags RWX. What that means is the stack is executable. Anything that you place on the stack can be executed as code, and that's exactly the reason why our shell code was being executed when we redirect the execution from the Rbp register to the shell code. Now when you enable NX, let's come back and examine what happens to this entry. I'm just changing the makefile here a bit. Let's remove this -z exec stack option. Okay, and let's remove the vulnerable binary from the current directory. There it is. Let's type make, and the binary should have been created. There it is. Let's type gdb-q vulnerable. Okay, let's type let's set up a breakpoint at main once again, and let's type checksec. If you see, NX this time is enabled. Now let's run the binary like we did earlier, and let's type VM map, and this time if you notice the stack, the X flag is not there anymore. What it means is stack is not executable, so even if you place shell code on the stack, it's not going to be executed. If you try to execute from a non-executable space, it is going to throw a segmentation fault. So even if you can place the shell code, when you try to execute that, it's going to cause a segmentation fault. So it's going to be useless. So what are the options what options do we have now? We have two options. One, either don't use the stack for your execution, or make the stack executable again and then execute your shell code. So let me show you both the options. Let me demonstrate how we can achieve both of these things. The first one is to execute something without making use of shell code on the stack. The second option, we want to execute the stack. We want to execute the shell code that is available on the stack. For that, obviously, we will have to change these flags from RW to RWX using our exploit, right? So let's first discuss the first one, which is return to libc. So return to libc is a technique which can be used to return the control to some functions that are available inside the libc library. So we are not going to execute the shell code that is available on the stack. Instead, we are going to execute some functions that are available on libc library, inside the libc library. So for instance, when you write a simple C program like system, when you write a simple C program with system function, that gets executed from the libc library. So from within our exploit, we want to achieve that. Let's see some examples here. I do have slides as well. In case if something is not clear, I can actually show you the slides. I'm trying to skip the slides a bit so that we can cover more concepts. So, so what I'll do is I will quickly write a C program, or rather we can copy it from here. We don't need to write it. Okay, let me just copy this system.c file. It's a very simple C program. We are just writing this here, system.c. So basically what this program does is it just execute this binsh shell using this system function. That's it. Let's compile this using GCC. and if you try to execute this, it should give a shell. That's it. That's a very simple C program. Let's load it using GDB and see how it works. GDB. If I'm going too fast, if you don't understand something, please ask your questions in the chat. Feel free. Oh, sorry, it should be system. Okay, now let's set up a breakpoint at main, and let's sorry, I'm just executing disassemble main, but I said breakpoint at main, so it may be confusing. Let's just view the disassembly of main. It's not breakpoint. So if you see this, we have a call to system at PLT. So basically this is a call to system function, and this just before this call you have something happening here. If you notice, there is an address which is being used, and it's just loading, it's just executing a LEA instruction, which is load effective address, into RDI register. So we have a call instruction which is calling system function, and just before that there is something that's being loaded into RDI register. In 64-bit systems, when you make a function call, the first argument gets loaded into RDI register. This is different from 32-bit systems. In 32-bit systems, I think you place everything on the stack, right? In 64-bit systems, you will be using few registers to place the first few arguments. I think the first 6 arguments will be placed in registers. I will explain what those registers are. If you have more than 6 arguments to a function call, then the remaining arguments will be placed on the stack. So in this case, the system function is taking only one argument, right, which is binsh. So that particular argument is being placed in RDI register. Now let's quickly examine what this particular entry here, 0x2004, is being shown by Jeff or GDB for us, just to make things simple. So let's just examine what we have. x/s. So we're just going to see if there is any string here, 2004 address. I'm just checking what we have at this address, because this is being loaded into RDI. Look at that. That's the argument we provided to system function. So binsh address is being loaded into RDI register, and once that is done, the system function is being invoked. When the system function gets invoked, it takes the argument from RDI register. That's the first argument, because it's in RDI register. I think the second argument goes to RDX or RBX. I'll show them when we get into that. The first argument but goes to RDI register. Okay, now there is another way you can check this. Info registers RDI. I think this is because the program is not being run. We can actually step through. Let's set up a breakpoint at main and run it, and we can actually do a single step until we reach the call instruction. Now we can actually check what we have inside RDI register. So IR command is info registers RDI register. If you don't specify the register, it will show all the registers. If you specify a register, it is going to show only that register. So currently it is not sure why this is not. Okay, let me. Okay, this is the address that is being placed there. Now let's run the binary once again. SI, and one more GDB shortcut. I'm not sure if it is a GDB shortcut or Jeff shortcut. You typed SI earlier. Now you want to type it again. You don't need to type SI once more. You can just hit enter. So the previously typed SI will be automatically executed. So I'm just hitting enter here. Now we are about to execute the function call, and if you look at the RDI register here, this is the same address that we were seeing earlier using the info registers command. And if you notice, it is basically pointing to this binsh string. So all I'm trying to show here is how function calls are made in 64-bit systems, the calling conventions. So RDI register is going to be used for the first argument. Now this is essential to understand the return to libc technique, because we are going to do the same thing using our exploit. We'll have to call the system function, and we will have to provide a pointer to binsh to that system function within our exploit. So obviously we will have to place that pointer in RDI register, right? So let me just show you some slides here before we get into that. So this is going to be the return to libc technique. So this is the plan for our return to libc technique. So the plan is, we will place some junk in the beginning, and then when we reach Rbp register, we will place the pointer to binsh string into RDI register. I hope it makes sense. I hope it is clear. See, we need to call the system function using our exploit, and the system function requires binsh as its argument. So we will have to place that binsh pointer to that binsh into RDI register using the exploit. How can we do that? We will have to pop that address which is pointing to binsh into RDI register, because system function takes it from RDI register. So to place it in RDI register, we will have to use some gadget. In this case, I'm going to use pop RDI ret gadget. If it is confusing, when we do it, it'll be clear. And when you execute this pop RDI instruction, whatever the value that is on the top of the stack is going to be popped into RDI register. So on the top of the stack, we are going to place the address of binsh, right? So when the pop RDI gets executed, whatever the value that we place on the top of the stack is going to be popped into RDI register. So obviously in this case, we will place the address of binsh. So that part is done. Each gadget must end with a ret instruction when we write any return-oriented programming. When we create any ROP chains, each gadget that we use should end with a ret instruction, because if you remember, when ret instruction gets executed, whatever the value that is on the top of the stack will be loaded into Rbp register. Here, after the pop RDI instruction gets executed, after RSP is popped, the value being popped, pointed by RSP is popped into RDI, the RSP goes here. So this becomes all of these will both of them will go down. So RIP and RSP will go down, and RIP will be pointing to the system function. So basically, once this pop RDI ret gets executed, RIP will be pointing to this system function. So the system function gets executed using the value that we have placed earlier into RDI as an argument. Now I will try to show this practically using by constructing this exploit from what we have earlier. So I'll just quit the screen, GDB, and let's copy gets exploit. It's going to be pretty simple if you understand, and let's save it as exploit1.pl. We are going to use a bit of return-oriented programming in this example, and after this return to libc example, we are going to do a lot of return-oriented programming when we try to execute shellcode on a non-executable stack. Okay, for now I will probably comment it out. I will comment out the shellcode and nop because we don't need it. We are not going to execute shellcode on the stack. Rather, we are going to use the functions which are already available in libc. So we need, let me also comment it out, and we need junk. I'm just rewriting that with 256 A's. So we have 256 A's and we have 8 B's to overwrite RBP. And the next one that we are going to write is the address of pop RDI comma ret instruction. How do we find it out? Let me just so if you notice, this is the libc location. We can find out these addresses within libc. So I'm just copying the libc library into this nx directory. So we do have libc library within our current directory here. If you notice, libc-2.31, and within this libc library we are going to search for those instructions. So for that I'm going to use another tool called Rbp. Rbp is a tool that can find gadgets for us. Typically when we write return oriented programming, when we create ROP chains, we use Rbp a lot. So I'm going to make use of Rbp a lot in this training. So I'm just hitting enter. This will load Rbp for us. Now the file in which we want to search gadgets is libc. So I'm just typing file space the libc library, which is in the current directory. Hit enter. It's going to take a bit of time because it contains a lot of, it's huge. It contains many gadgets. Okay, as you can see, the libc library has been loaded. Now there are the easiest way to search for gadgets is to type search, and you can actually specify the depth. So I typically prefer to specify the depth as 1. I'll show you what happens if you don't specify, and I'll use the instruction that I want. So in this case, what we are interested in is pop RDI, because we want to pop the address of binsh into RDI register, which is required by system function. So if you hit enter, look at that, it has given us few gadgets, and I'm interested in this gadget because it is looking simple. It doesn't have any complexity. Typically I prefer to pick gadgets that are simple and the gadgets that do my work. So in this case, it will do pop RDI, which is going to pop the value into RDI register. So that is what I want. And it has to end with ret instruction so that it will transfer the control to the next available gadget. In this case, the address of system function. So what I'm going to do is I will just copy it here, and actually we overwrote the exploit in a different directory. That's fine. So let's copy getsexploit.pl and let's call it exploit1.pl, and let's open this using Vim. And this is the address that we have gotten from libc. I'm just pasting it here. Here it is. Now if you notice, I'm not sure if you noticed or not, this is just an offset. So that means this particular gadget is at this much of distance from the base address of libc. What that means is it's not an absolute address, it's just a relative address to libc. So to get the actual address to this particular gadget, we will have to add this particular value to the base address of libc. Let me just go to this directory here, and let's create a new variable called libc_base, and this is where we are going to specify the libc base address. Any ideas how can we get the base address of libc? Any ideas from anyone? Meanwhile, let me just fix this. We need 256 A's. Okay, seems like there are some answers. Okay, Dazi says LDD and Dharmendra says VM map. Okay, we can actually use both. I'm just going to use VM map. Okay, so we are done with this. We have libc base variable and we have 256 junk, 8 base, and here, as I mentioned, we will have to add this to libc base. Otherwise, it's not going to work because it's just a relative address. It's not the absolute address. So we will have to add it to the base and then we will have to do it. So let's also remove this knobs and shellcode. The exploit is not complete. We will have to first identify the libc base and then we will have to place it here. So let's do one thing. Let's quickly go to one of let's navigate to NX. Let's load the vulnerable binary using GDB. Let's set up a breakpoint at main and let's run the binary so the breakpoint will hit. Now we can use vmmap command to get the libc base address. So if you see this is the libc base here. This is going to be the libc base. I'm just copying it here. 7DC6000. I will also try to close unnecessary terminals just to avoid confusion. Okay, so let's place the value here at libc. So Perl will automatically do the calculations for us. We don't have to do the additions for all the addresses. That's why I'm just using a variable here and let it do the heavy lifting for us. Okay, so that part is done. Now the next step is to find out the address of binsh string and the address of system function, because we have just gotten a gadget that can load the address into RDI register, but we don't have the address, the actual address. So let's find out the address of binsh. So to find out the address of binsh and the address of system function, we can actually do, there are a few ways we can do that. For the binsh, we can actually use strings command on the library, on this libc library. For the system function, we can, where is my vmmap output? Yeah, it's here. So here I'm just going to use xinfo system. So this command should give us the address of system function. If you notice, this is the actual address of system function. So I'm just copying it. I'm just copying it here. This is the absolute address. You don't have to add it to the libc base. Okay, so I'm just going back to my exploit and I'm just placing it here. Remember, the immediately after RIP, we need to have the address of binsh. So we will fix that part in a moment, but just remember that. Don't get confused because I'm just placing the address of system here. System, and the RIP contains pop RDI ret. Now pop RDI instruction should pop the address of binsh string, but immediately after this we have system. So here we should place the address of binsh string. So I'm just adding that here. Okay, so let's find out the address of binsh now. So I'm just going back to the Rbp shell here. Just in case if you're wondering, there are multiple tools available for finding gadgets. I have been using this Rbp for a while, so I like to use this. So instead of, we can use Rbp, or instead we can also use something like strings binary and all that. So I'm just going to use strings. I'll just take a look at the help options. If you see, -a is to scan the entire file, so I'll just use that option. And we want to print the location of the string in base 16, so I'll be using -t x, so that I'll get the address in base 16 format. And yeah, I think that's pretty much it. So let's just use strings command. Strings scan the entire file, -t x, so that we will get the offset in base 16 format. And let's use grep binsh. Hit enter. Look at that. This is the offset to binsh from libc within the libc library. So once again, we will have to add it to the base address of libc. So that's the reason why I have already created this entry here, where I'm just going to use libc_base plus this value. I think we are pretty much done. We can actually use this to exploit the binary already. We can get a shell, but we can make some cosmetic changes as well. But for now, let's quickly test the exploit to see if you're getting a shell or not. So let's use, for this we'll have to disable ASLR. Just remember that. We have already disabled it, so it's not a problem. Cat vulnerable. There is a segmentation fault, and there is a reason for that. Let me open up my slides. I think I don't need to open up the slides. There is a reason for that. Let's probably produce the payload from this exploit. So I'm just creating a new payload called payload1 within this directory, and let's use gdb /vulnerable-q, and let's set up a breakpoint at main. And we can actually run the binary using if you remember, we were using a different way earlier, because we were taking the command argument as the input. But in this case, once again, it has to read from the std in, so that's why I'm passing it like this. So we can just run here, and let's set up a breakpoint at one function. Like we did earlier, we'll just set it up at ret instruction, and let's continue with the execution. So we are about to execute the ret instruction, and if you notice, after this we are about to execute pop RDI, which is what is expected, because we placed this address in to override the Rbp register, and it is basically redirecting to pop RDI gadget. And if you remember, I was telling you that okay, let's probably do an SI first, so you will better understand this. Okay, now we are about to execute pop RDI, right? What does it do? It basically pops the value on the top of the stack into this RDI register. What is there on the top of the stack at this point of time? If you notice, there is some address which is pointing to binsh, and that's what exactly we wanted in RDI register. So if you execute SI, RDI basically contains this address, which is going to point to binsh. And once that is done, it is executing the ret instruction. If you remember, our gadget contains pop RDI, ret. So when the ret instruction gets executed, it is going to land on the next instruction to be executed, which is, in our exploit, the address of system function. So we are about to execute system function, and we have the required value in RDI register. What it means is we have everything properly set up, but still the exploit is failing. Is it clear? We have everything we require, right? Anything we are missing? Any idea why we are? Because we are able to land on system function properly, and we have managed to set up the RDI register as well. So any guesses why it's failing? while you're thinking, I'll just have a sip of cold drink. Return from system is causing failure. Actually, no. Let's continue the execution and see what happens. Will that give you a hint of what's happening? Let me just type continue. If you notice, we don't have any other breakpoints, but there is a segmentation fault. If you see this, sig v, and we are still inside the system function. We are not. See, there are a few more instructions to be executed within system function. So there is some problem within system function itself. And if you notice, this is exactly the instruction that is causing the issue. I'm not really an expert in terms of identifying these low-level issues. So I was just using Google to help me with this. So I'll just copy this. And if you notice, there are few links here. There was one blog which has explained this very well. So I'm just trying to look for that. It's not this. Yeah, so I think it's not, this is not the blog, but if you see this, this particular instruction causes an error when there are stack alignment issues. So to fix this, basically there are a few ways. Instead of using the pop RDI ret at the top of the, without overwriting the RIP immediately using pop RDI, we can rather execute a ret instruction first, so that the stack alignment issues will be solved. There is a very good blog which talks about what stack alignment issues are and what this instruction does and why it causes these problems. I'll share that link during the break time. I couldn't find it here. But the problem, the solution to fix this problem is to use a ret instruction in our exploit. Where do we use it? Let me just quit. I also have it in the PowerPoint. Let me show that. So this is what we have done so far, right? So this is all good. I did not add this exit address, but I leave that as an exercise for you. I'll let you know what exit is and why we need to use that. But even without using exit function, we can still get the shell. So if you see this, this is what we have earlier, and we are now going to add one more gadget here, which is ret at the top. So after filling up the junk, after overwriting Rbp register, instead of immediately writing with this address, we are just going to use this gadget so that the stack alignment issues will be fixed. Okay, so what I'm going to do is I'll once again load Rbp. I should not have exited, so I'll just use Rbp, probably on a different shell. You don't need to load the entire binary. You can also use the command line flags to search for a specific instruction, but I prefer this way because you will have control on the depth you want to search for and all that. If you remember, I was telling you about the depth, which is one is what I have used, right? So let's say I don't use 1. Let's just look for the ret instruction directly. Look how many instructions you have, how many gadgets you have gotten. The reason is we are not limiting the depth. It's showing us as many instructions as possible. So this particular depth is basically kind of filter so that you don't want to have longer gadgets. So I'm just specifying depth this time, and look, the longer instruction, the longer gadgets are, the gadgets with more number of instructions are not there anymore. Now this is the gadget that looks pretty simple. All we need is ret instruction, so I'll just copy this. So this is the address I'm going to use. Let me just go back to NX. Let's open up our exploit, which is exploit1.pl. And just before this pop RDI, we are going to place this pack once again. It's an offset, so we'll have to add it to the libc base. Right. Okay, so let's save the file. Hopefully this time it should work. There seems to be some problem with the exploit. Let me check what it is. Libc base is fine. Junk seems to be okay. Right. Oh, okay. There is a comment missing here. That's the problem. Okay, so let's run it once again, and let's type ID and look at that. The exploit worked. Now, if you type exit once again, look, when we type exit, there is a segmentation fault. Because after the system function is executed, the program doesn't know where to return to, so it's not able to gracefully exit. So for that, we will have to provide the address of exit function in the next line here. Here, if you notice, immediately after the system address, we are presenting the exit address, so that when you exit from the shell, it will gracefully exit without throwing any segmentation fault. At this particular point of time, after the system function is executed, when it finishes, it doesn't know where to return, so it is just causing a segmentation fault. If you specify exit's address, it is going to gracefully exit. So all you have to do is you will have to use GDB or Jeff to find out the address of exit function and add it to the exploit at the end. That's it. I will leave that as an exercise for you, but I won't modify the exploit, but I'll show you how to find out the exit address so that you can just use that in your exploit. Okay, Sachin Grover says comment red. I have just seen that. Yeah, I have already fixed that. Thanks. Now let me just go back to this, and just like how we did earlier, we can just use xinfo exit. There it is. If you see, this is the address of exit function, and you can simply add that at the end of the exploit. So that should fix the segmentation fault when we return from system function. All right, so that is return to libc, and we are done with that as well. So we managed to bypass NX. If you remember, this binary has NX bit enabled. The stack is not executable, but instead of executing shellcode on the stack, we tried to execute system function from the libc library. Since there is no ASLR enabled, we managed to get the base address by using GDB, because the base address never changes since ASLR is disabled. Right, so these are the conditions for this exploit to work. Number one, stack is disabled, but we still managed to execute some code. Stack execution is disabled, but still we managed to execute some functions by not touching the stack. Right, we instead used some functions from libc. But there is a disadvantage here, right? If you think of it, you can only use whatever the functions that are available on libc, because you're completely relying on the addresses that are available on libc. Now, what if it doesn't have bin sh string, or what if it doesn't have something that you need? So in such cases, once again, we will still have to rely on executing the shellcode. I mean, if you want to have granular control on the exploit, I think you still need to execute shellcode on the stack. Let's say the requirement is to execute shellcode on the stack, and you don't want to execute system function. then in such cases we will have to purely use return oriented programming, and we will have to enable this executable bit on the stack. So that's how we can execute shell code even when the NX bit is enabled. So that's our next demo. Since we are having a very short amount of time, I think I will skip this return to PLT. I'll skip the return to PLT for now, but if we have time at the end, I'll try to cover that. The reason is this one, the format string vulnerabilities and the other two concepts are slightly complicated, so I'll try to cover them in this training. So the next one is return oriented programming. So what I will do now is I will write another exploit that will still execute shell code on the stack even when the stack execution is disabled. And we are going to develop this Rbp chain from scratch. So let's get started. Let me open up my VM. Let's create a new directory called Rbp. So we are going to basically create a Rbp chain which will enable the X bit. If you remember, we have RW and dash on the stack entry when we tried using vmmap command. That means stack execution is disabled. So we are going to enable that through an exploit, and then we will run the exploit to execute the shell code. Okay, so let's navigate to Rbp directory, and let's once again copy everything from the directory above this into the current directory. Okay, we are all good. Now within this, we are basically using the same binary, vulnerable, and this vulnerable binary has stack execution disabled. Okay, now before we start writing our Rbp chain, I think I will try to use about 20 minutes to do this because we want to use at least 1 hour for the remaining concepts. If I can't finish, I'll try to extend it by 30 minutes. So if you are comfortable staying back, you can stay back until we finish all the exploits. Okay, so the next one is return oriented programming. As I mentioned earlier, return to libc bypasses NX, but it limits our ability to execute custom code. We can't execute the shell code of our choice. And what if we want to execute shell code on the stack even when NX is turned on? That's where we need to somehow make the stack executable again. I think this is the Trump statement, and for that we are going to use return oriented programming. Now we are going to create a manual Rbp chain to enable execution on the stack, and then we'll execute the shell code using that. Now there are a few things that we need to understand before we start writing the Rbp chains. First, we are going to use a tool called Rbper, which I have already introduced to you when we discussed return to libc, and we will have to construct the stack by strictly following these conditions. So when I build the Rbp chain, I'm going to follow these conditions strictly. Number 1, place the gadget chain to disable NX and jump to shell code. So that's the high level idea, right? We want to chain some gadgets. When I say gadget, it's basically some few instructions together is one gadget. We have already seen that, right? Pop RDI, ret is one gadget. Similarly, we will need to find out some instructions which will do the job for you. And the next step, each gadget must transfer control to the next gadget. If you remember return to libc attack, we have used this particular concept already. The gadget that we were using was actually making use of ret instruction at the end. So whenever we select a gadget, we will have to ensure that the gadget has ret instruction at the end. Number 3, consider the gadgets ending with ret instruction. So that's the same thing. And number 4, all required parameters are available on the stack or the relevant registers. So this is the most important part. Just like the system function, when we crafted the return to libc payload, we tried to arrange the stack in a way that the system function has everything ready by the time it gets executed. For instance, we have placed the address of binsh string in RDI register, right? So similarly, we can basically use, we should basically set up everything before we invoke any functions, so that the function can actually pick up the required arguments from those registers. And then we will place a lot of bytes on the stack. Actually, there is a typo on the 5th point. It's not space, it's place. We will place a lot of bytes on the stack, so space is definitely a requirement. So when you are writing your exploit, make sure that you are doing it where you have enough space. And then the last one, if there are any instructions in the gadget that we do not need, we will have to carefully handle them by filling with the right amount of data before reaching the next instruction. So this is important because when we search for gadgets, it's not guaranteed that you will find what you're looking for. Sometimes, let's assume that, let me take an example. Let's assume that you're searching for this gadget, pop rdx, ret. But unfortunately, you did not find this gadget. Instead, you found this gadget, pop rdx, pop r12, ret. If you notice, we don't need this pop r12 instruction in this gadget. We don't need it. However, we will still have to live with it because the gadget, the address that we found contains this instruction. We can't remove that from there. So in our exploit, we will have to carefully manage such unnecessary instructions as well, right? So when we get into this kind of gadgets, I will show you how we can manage such gadgets. Okay, and that's pretty much it. Now, the next question, we want to turn the stack into an executable one. How can we do that? So there is a function called mprotect in Linux. We can use this mprotect function to actually change the permissions of a memory space. So let me quickly show you the man page of mprotect. Man to mprotect. Basically 2 is used for system calls, so mprotect is a syscall. So I'm just using man to mprotect, and if you notice here, I'm just trying to highlight this. If you notice, this is the mprotect function and it requires 3 arguments. So if you want to turn the stack into an executable stack, we will have to invoke this function mprotect with appropriate arguments. And if you notice, it requires 3 arguments. The first one is the address, the second one is size, and the third one is an integer value which says the protection, how to say that, it basically decides whether your memory space has to be readable, writable, or executable. So that's an integer value that decides that. That's the third argument. And the first argument is the address at which you want to change the memory protections. And the second one is the length. So how much of your memory should be changed? How much of your memory should be affected by this protection? So essentially, we are basically trying to execute this particular function to change the stack's permissions to an executable one, right? We don't need to change the entire memory region. We can basically change only the space where we are going to place the shellcode. So the first one is going to be the base address of the stack in this case, because the address that we are going to change the protections on is stack, right? So basically we are going to place the base address of stack here as the first argument. The second argument is the length. How much memory space is going to be affected by this change? we are going to pick some number that I'm comfortable with. It doesn't have to be that. It doesn't have to be the case in all the cases. But when I was doing 32-bit exploit development, I came up with some value which is pretty good in 32-bit exploit development. So I'm just going to use the same value here. But as I said, you can change it to a different value. You can basically use your own length. And the third one is the actual protection. If you see this, prot none, the memory cannot be accessed at all. If you see prot read, if you basically use this, the memory can be read. And prot write is used to say that the memory can be modified. And prot exec is memory can be executed. Now, if you see this, a bitwise OR of other values can be used to specify what protection mechanisms you want to enforce on the stack. What that means is, if you want to have read, write, execute all together, basically you can just use a bitwise OR of these three, which turns out to be the value 7 here. So basically, if you place 7 as the third argument, your stack will become executable. So to summarize, we are going to execute this mprotect function with 3 arguments. The first argument is going to be the base address of the stack. The second argument is going to be the length. And the third argument is going to be the value 7, so that the stack becomes read, write, execute. So the stack will have those flags read, write, execute. Right? So let's go back. Okay, so if you remember, I was talking about the calling conventions. When you call a function, how do you specify the arguments? RDI register contains the first argument. We have already discussed that when we discussed about return to Libc. And the second argument goes into RSI register. And the third argument goes into RDX register. That's it. Once that is done, we can simply call mprotect function. Now, we can manually go ahead and examine we can manually go ahead and understand this mprotect function using GDB, but since we are running out of time, I will try to directly write the exploit. So let's try to follow these instructions. Let's try to follow this concept, and let's try to build an exploit using this. It's pretty easy. Don't get, try to pay some attention here while I'm writing this exploit. It's pretty easy to understand. Okay, so the first one, we are just going to copy exploit 1, right? So here we are. We can just use the same exploit. I will do everything step by step. I won't copy anything from anywhere, so that you will be able to easily understand everything. The first step, we are writing 256 A's. And we are writing RBP here, and after that we need to have some gadget that prepares our registers. So what are the registers that we are currently interested in? RDI, RSI, and RDX. So obviously, if you want to pop something into RDI register, you're going to use you're going to use a gadget which contains the instruction pop RDI, ret. So this is what you're interested in. Similarly, when you want to place some value into RSI register, pop RSI, ret. Don't get confused with the instruction pop RDI. What it means is the value that is on the top of the stack is going to be popped into RDI register. I think there is some confusion. A lot of people get confused about these instructions, because when we talk about push and pop, we only think about the stack. We push something onto the stack and we pop something off the stack, right? But when we are using this pop RDI instruction, what that means is whatever that is available on the top of the stack is going to be popped into this RDI register. So what you place there on the top of the stack is going to be popped into this. Similarly, when you want to place something in RSI register, you can basically use pop RSI. Similarly, when you want to place some value in RDX register, you can use this gadget. Now, obviously, the next immediate goal is to identify the addresses of these gadgets, right? So let's go there and search for these addresses using Rbp. Once again, I'm just going to use Rbp and libc library because ASLR is currently, another thing to note is ASLR is currently enabled. So let's start searching for pop RDI. So that's the first. And if you notice, we already got one gadget here. So I'm just copying it there. And let's place it here. So we got one address. We are done with that. Next address, pop RSI. So we will just search for pop RSI. Interesting, pretty easy. We got a neat gadget, nothing complex, just one instruction pop RSI, which is going to pop something into RSI, and a ret instruction so that the control will be transferred to the next gadget. Okay, so when this gadget gets executed, it is going to transfer the control to the next gadget based on the value on the top of the stack when the ret instruction gets executed. That's the reason why we are looking for gadgets with the ret instruction at the end. Similarly, we want pop RDX. Let's search for that. There is a typo. I'm just typing it again. Look at that. We did not find what we wanted, so let's increase the depth to 2. This is where I increase the depth. Only if I don't find the gadgets with depth 1, I typically increase the depth. If you notice, the gadget is not ending with ret, so I don't want to use this instruction. So let's increase the depth to 2 and hit enter. And there it is. There is one instruction that we found here. I'm just going to use this pop RDX, pop R12, ret. If you notice, we only want this gadget, pop RDX, ret. But unfortunately, we found a gadget with some additional instruction, which is having pop R12. So we will have to handle this as well. Even though we don't need that, we will have to handle it. Otherwise, the exploit will fail. So the first 3 steps are already done. We can start building our exploit now. Now, once you place appropriate values into RDI, RSI, and RDX, we need to have the value of the address of mprotect function, so we can directly call that. So what the next step we need to do is find out the address of mprotect function. That's one step. The number 2 is we need to find out what values we want to place into these registers. We already explored that using the man file of mprotect. So RDI should have base address of the stack. The second register, the RSI, should have the length, which is, I'm going to use 0x01010101. In 32-bit exploit development, this is the maximum value that you can use when you call this mprotect function. This maximum value is basically the value that doesn't cause any null bytes. You can use any other value of your choice. As long as your shellcode is being placed in that region, you will not have any problem. So in 32-bit exploit development, this is the maximum value that you can use without causing null bytes. So I'm just going to go with the same value, but you can actually increase the value if you wish to do that. And the last one, as I told you, is going to be 7, because this will turn the stack into read, write, executable. Okay, so let's find out the base address of the stack and the address of mprotect. And once we are done, we are pretty much done with the exploit. We will be able to bypass NX. So let's go back to GDB. So how can we find out the address of the base address of the stack? Any answers? I need answers to both of these. How can we find out the base address of the stack, and how can we find out the address of mprotect? Please. VMMap. Yes, we can use VMMap to find out the base address of the stack. That's right. What is this Rbp and xinfo for mprotect, that's correct. Okay, so we can do that. So that means you are able to understand what I'm doing here. Thanks. Okay, so let's go back to the virtual machine and let's use GDB for finding out both. I'm just navigating to nx drop. Yep. gdb./vulnerable breakpoint main. Let's run it and let's use vmmap. See, I'm just setting up a breakpoint at main and then starting the binary to be able to get the memory maps. So let's also clear the screen so you will be able to see everything at the top of the screen. vmmap, and this is the stack entry, and currently it's not executable, and this is the base address of the stack. So I'm just copying this and I'm going to paste it here. So one part is done. Next step is to find out the address of mprotect. So let's try xinfo mprotect. If you notice, this is the address of mprotect. So once again we can copy it and we can place it here. That's pretty much it. We are pretty much ready to write the exploit. Once we are done with crafting these things into our exploit, I think we are pretty much done. Okay, let me just quickly confirm that I have done everything right. Yep, everything looks fine. So let's just go here to our exploit. Okay, the first one, let's replace this ret with I think I'll just comment it out. Okay, and we will just start from here, which is pop rdi ret, because I think we have taken the same address. Yep, we have taken the same address that we already have, 26b72, and we already have that 26b72, so I'm just going to use that. That's fine. And immediately after that we will need to place the base address of the stack, so that will be popped into RDI register. So what I'll do is I will use the base address of the stack, which is here. Okay, anyway, I'm just here, so let me just change it to this. I'm just changing the comment first, and then let's change this address. So this is base address of the stack itself. We don't need to add it to libc base because we are not getting this address from the libc. It is just the base address of the stack. If you notice, these addresses have multiple null bytes, so that's why we are not using strcpy. If you are using strcpy, we will have to also deal with null bytes in this case. I have a 32-bit exploit development course in which I have shown the same exploit but using strcpy, in which I was also handling these null bytes and all that. Okay, so the next one is, okay, we are done with base address of the stack. So what's the next step? We will have to place this gadget. So let's copy this. So this will place the length in RSI register. So let's use junk pack and libc underscore base plus this one. So this is pop RSI comma ret. So what do we want to place in RSI register? That's the length. So let's add another line here, which is going to contain the length. So the length is 0x01010101. As I mentioned earlier, this is just a value that I'm comfortable with, and if you come up with some other values that work for you, you can just still go ahead. I don't want to experiment during the training, so I'm just not using a different value since I've tested everything using this value. And the next one is this. So I'm just going to use this gadget so that we will have RDX value set as well. So let's use junk pack. Remember, once again, this value is from libc, so we will have to add libc base to the address. Okay, so this is, let's also make sure that we are properly putting semicolons and all that, otherwise it's going to be very hard to troubleshoot things. Please let me know if you find any mistakes. So this is pop RDX. Okay, looks fine. The next step is simply to pop the value 7 into this RDX register. libc underscore base plus, sorry, there is no libc base required, it's just the value 0x7. Okay, so this is RWX. And finally, we don't want system address, instead we want mprotect address. So I'm just copying this. And let's replace this with this. We are pretty much done. The next step is to redirect the execution to our shell code, right? How do we do that? So let's first put some junk here. We can actually pick some address that we have used earlier. Let's say let's go to simple buffer overflow. Let's go to gets. Let's get the address from here. So I'm just going to use the same address that we have used earlier. So look how different the exploit now is when we want to bypass NX. Earlier it was just this line, we directly had this. Now before executing the same line, we are executing multiple other instructions. Okay, so this is going to be the address of shellcode. Obviously we will have to uncomment the shellcode and nopsled. So I'm just uncommenting this, and let's comment out these 256 A's. Okay, so if you notice, we have nopsled, shellcode, and we have some A's minus the length of the shellcode and nops, and then we have RBP, and then we have our complete ROP chain. Now once mprotect returns, it does all the job for us by enabling executable flag on the stack. Okay, so let's copy this address. Okay, we already have it here, so we can use that when we debug the exploit. Now next we need to print nops, shellcode, and junk. All right, let's save the file. Hopefully everything is correct. Now let's produce the payload. And just to ensure, I will show you the debugging part, but just to check if the exploit is working fine or not, I'll directly run it without GDB. Shellcode spelling. Okay, let me check. Oh, thanks. It's a terrible mistake. Okay. Okay, basically someone in the chat told me that the shellcode has a spelling mistake, so I just corrected it. It's Shruti. Let's save it. Now let's try to execute it. Exploit 1.pl cat vulnerable. There is a segmentation fault. Any guesses why? Any guesses? If you remember, we have this instruction where we managed RDX but not R12. That's what I was trying to explain earlier. So when we have gadgets like this, your exploits will fail if you don't handle this. If you remember, after this address, we simply added 7, which is going to be popped into RDX, but we didn't specify anything that gets popped into R12. So let's go ahead and fix that. Let's exploit 1.pl. And here, after this line, so when this line gets executed, what happens is pop RDX is going to be executed, and this value 0x7 is going to be popped into RDX. But next, there is another instruction within the same gadget, which is pop R12. So we can actually place some dummy value immediately after this, so that value will be popped into R12. If you don't do that, this value of mprotect will be popped into that, so that's going to cause an issue. That's why the shellcode is not being executed. So let's add some junk here. So I'll just use 6As. Remember the canonical addressing, we can't use 8As here. And let's save the file. Let's try to execute it. Still there is a segmentation fault. Let's check. Oh, generate payload. No, we don't need to generate payload because we are directly passing the exploit itself. What we can do is we can remove the core file and we can actually try to check if it is, or we can simply debug. Let's check. Exploit 1.pl payload 1. Let's use gdb /vulnerable -q breakpoint at main, and let's run the exploit. I mean, let's run the binary with the payload, and let's set up a breakpoint at the ret instruction of the vuln function like we did earlier, so that we will land on the mprotect function hopefully. And let's continue. Okay, if you see this, we are about to execute our first gadget, which is pop RDI. Let's type si, and RDI now contains the base address of the stack, hopefully. Is it correct? Is it the base address of the stack? 44D0. Looks like it's different. Have we already executed pop RDI, or oh, we are about to execute, so that should be okay. Okay, so if you see, the RDI register has the base address of the stack, which is fine. The next instruction we are executing is pop RSI, so let's type si. Okay, so that looks okay. It is going to be having this value 01010101, which is what is expected. So let's type pop RSI. So RSI register now contains the value that we were expecting, which is fine. And the next instruction to be executed is ret and pop RDX. So pop RDX, when it gets executed, the value 07 is going to be placed in RDX. Let's type si. So let's quickly check RDX, and it has the value 7. So all the arguments for mprotect are properly set up. Everything looks fine until now. Now let's type pop R12, and let's check what R12 has. Seems like R12 doesn't contain our A's. So that's where the problem is for now. I'll just keep it here and I'll try to make changes to the exploit in a different tab. I'm not sure why it's not coming there, because we updated the exploit, right? Yeah, R12 should contain these A's. Let me quickly check if my I have an existing exploit which I have done earlier. Let me check if we have done everything as is. I just want to save time because we have very less amount of time now. Cat rop 1.pl, rop 2.pl. Yeah, looks fine. Probably we will use 41s in hex format. Let's check if it helps. So I'm just going to update the exploit here with 641s. 0x41, 41, 41, 41, 41, 41. So there are 641s. It's essentially the same, 6 A's. Probably passing it as a string is causing the issue. I'm not sure. Let's check. So let's once again execute it. Exploit 1.pl, cat, and vulnerable. So segmentation fault, which is a good news actually. It's not a bad news because we have placed an incorrect address, if you remember, to the shell code. So let's try to execute it once again, and let's try to get a segmentation fault, and let's examine the core file 50gx, gdb-core x/50gx rsp minus probably 280, looks like 290, maybe 300, because I'm just looking for my NOP sled. I couldn't find it. Maybe 320. Yeah, so we can probably use this address. If you notice, this is pointing to the NOP sled. So actually we can even try further, 324 or 322, 320. Probably we'll go with this address, which is looking okay. I'll copy this. And I'll update the exploit. There it is. So that was the problem earlier. We were having a different, we intentionally gave a different address just to get the segmentation fault so that we can use the core file to understand what's causing the issue. Right now, I'll just quickly, I hope you understood this. I'll quickly run the exploit once again just to confirm that it's working fine. Hit enter once again and type any commands, and there it is. Okay, so the exploit is working fine. Let me quickly use GDB to show what happened to the stack. Okay, pack expects hex. All right. Yeah, that's what I have done in my exploit, but I think I've forgotten that. Nice. Now let's use GDB vulnerable -q, set up a breakpoint at main. Before this, let's also set up exploit 1.pl payload 1. I think I'm just going to quickly go through GDB and I'll show you what happened in the background. So we have set up a breakpoint at main. Let's run the payload. Let's run the binary with the payload. And we are currently at main. Let's set up a breakpoint at ret instruction once again, which is here. All right, so let's continue. And if you notice, we are about to execute pop RDI once again. Let's type SI. Next, we are about to execute pop RSI. You just keep noticing here the next instruction to be executed. I'll just keep hitting enter. Pop RSI is the next instruction to be executed, which is the instruction from our gadget. And next two instructions are pop RDX and pop R12. If you notice, R12 now contains the 6 A's. And after that, we are jumping onto mprotect function, if you notice here. So that means mprotect function is about to be executed and we have properly set up all the arguments that it requires. Now, before we execute mprotect, let's quickly check VM map. If you notice, the stack is still not executable here. RW is there, but not X. So let's type SI. Let's type SI a few more times. And let's type VM map once again. Let's just check. Look at that. So after executing mprotect, a few instructions inside mprotect, the stack became executable. And when the mprotect returns back, it is going to call the address where the shell code is placed. So the execution will be redirected to the shell code, and then we are getting a shell. So this is how we can manually create drop chains. When you use Mona, basically this is what it automatically does in Windows. It will try to find out all the gadgets that you need, and it will try to place them in one order for you. You will just copy that and you will just place it in your exploit. Okay, so that's return-oriented programming fundamentals. Any questions so far? If not, I will move on to the next topic, which is bypassing canaries and ASLR and NX altogether. So this is the stack structure of our exploit. We have already done that. As I said, I'll just skip the PLT and GOT from this training because we have very less amount of time. We have 1 hour. I'll try to cover the remaining. If there are no questions, I will move on to the next one, bypassing stack canaries and bypassing ASLR and NX all together in one exploit. I will try to write only one exploit to bypass all of this. That covers everything that I have planned. Okay, I assume there are no questions because I don't see anything. Can we move on to the next topic? Okay, I'll need a 2-minute break. I'll be back. I'll just get some water and come back. Meanwhile, I'll open up the exploit POC if anybody wants to see that. Here it is. Also, since I'm taking a short break, if you haven't, please help us tweeting or putting some messages on the social media if you're enjoying the training. If you notice, we have very less amount of people. The reason is not people are not interested, but we wanted to reduce the size of the audience only to those who are really interested in attending the training. So basically that's the reason why we set up a pre-training challenge. If people are really interested, they would basically solve the challenge and show up for the training. Otherwise, since it's a free training, we got a lot of requests for attending the training, but that's how we filtered people. All right, so please help us tweeting if you're enjoying it. All right, so let's get started with the next topic. We have about 45 minutes, but please expect that there will be a delay, like probably by 15 minutes. So let's take another hour. We will take 1 more hour to finish the next exploit. So, oops, I have closed the slides, I think. Anyway, so the next topic is to bypass stack canaries and ASLR using format string vulnerabilities and buffer overflow. So before we get into that, let's first understand the problems we have. First, let me just go back here and let's create a directory called full bypass. Okay, and let's navigate there. If you notice, we have been cheating a bit. We have disabled NX. Initially we disabled NX, later we enabled NX, but we still disabled stack canaries and we still disabled ASLR. So we have been cheating a bit. Now there is no more cheating. We will enable all the protections and then we will see if we can bypass them by chaining some vulnerabilities. Now, the first thing I'm going to use, I'm going to copy everything from the Rbp directory once again. NX Rbp, because that's the latest exploit we have. And I will just delete the core file and I'll edit the make file to have everything enabled. I will just disable this stack protector, no PIE and everything. Please pay attention for the next 1 hour, because this concept is bypassing all together at one exploit is going to be very complicated. So I will need your full attention here if you are still here. Okay, so let's save the file and let's remove the existing vulnerable binary and let's create it once again using make function. Make command, and there it is. We have a vulnerable binary. Now we can quickly type checksec vulnerable here. I have installed checksec even here in the machine. I hope I have installed it. Yeah, there it is. Look at that. All of them are enabled. Full railroad, Canary found, NX enabled and PIE enabled. Now we are going to deal with all of these in the next exploit. So before we deal with all of these, we will have to understand what are some of those protections that we are directly going to deal with. Number one, we are going to ignore PIE because it's not PIE is not applicable for us in our exploit. It's automatically going to be cleared off. We are also not going to deal with railroad. We are only going to deal with stack canary, NX and ASLR. So PIE comes into picture only if you use the addresses from within the binary. We are not going to use any addresses from within the binary. We will use all the addresses from libc library. So it's not a problem for us at this point of time. So PIE is out of scope for our exploit. Okay, so let's clear the screen and let's try to run the exploit. The same exploit that was working earlier, which is exploit.pl. We still did not enable ASLR, but let's see what happens. Cat vulnerable. Look what happened. The first problem we are now facing when we enable every protection is stack smashing detected, terminated. So this means we are not even able to proceed further to execute the shell code. So to be able to solve other problems like NX and all that, we first need to be able to override the return address, and then we will call the mprotect function using some gadgets and all that. But this protection is not even allowing us to reach that stage. So that means the first and foremost thing that we have to bypass is stack smashing. Stack smashing detected. I will explain how this is being done, but let's also enable ASLR now. I'm going back to ASLR directory. Let me use a different tab. Let's verify ASLR. Look at that, the value is currently set to 2. So what happens? What are some of the problems that we are going to face in the exploit that we have already created? Let's take the Rbp chain exploit as an example. This one. The first and foremost thing, because of stack canary, because of the stack canary that is detecting the stack smashing, we won't be able to overwrite. We won't be able to take control of ret instruction. I mean the saved return address, which is Rbp Register, because even before we take control of that, the stack smashing detection protection is basically stopping us from everything. That's one problem, so we will have to solve that. The problem number 2, NX is also enabled in this binary, so obviously we will have to go with one of these two techniques, which is return to libc or return oriented programming using mprotect function, right? So that's the second problem. Number 3, ASLR. Since ASLR is enabled, this libc base address is not going to be static anymore. This will keep changing every time you start the binary. So if you write this exploit with this particular base address as a static address, it's not going to work every time you restart the binary. So basically, the moment you start the binary, it's going to get some different libc base address, which is completely different from what you have in this exploit. So obviously that's going to fail. So these are the 3 problems that we will need to solve in this particular scenario. So first, I'm going to change the binary because it's a bit hard to exploit this binary with all these protections. So let me just copy another binary. Let me just copy another vulnerable program into this, which contains some memory leak problem. So we are going to chain those memory leaks, and we are going to leak the base address of the libc library, and then we are going to come up with a new exploit. Okay, so let me get the vulnerable binary. So this is going to be the vulnerable binary here. I'm just copying this. If we have more time, I would have explained everything with GDB and all that. Currently, I think we will have to skip some of the basics, but I hope you will understand. Like how the stack canary detects the stack smashing detection and all that. I'll try to show as much as possible. But yeah, let's compile this, and we should have a new binary here. And this particular program, if you notice, is vulnerable to 2 different vulnerabilities. It is taking an argument from the user, if you see argv1, and it is calling vuln function, which is this. And that user supplied input is being passed to printf function without using any format specifiers. That causes a format string vulnerability. When you have format string vulnerabilities, you can basically leak the addresses from the stack. If you're lucky enough, if those addresses that are being leaked from the stack contain any libc addresses, and Canary, the stack Canary, which is detecting your stack smashing attack, you can basically use those details to actually perform this buffer overflow attack, which is being caused because of the gets function. So that's what we are going to do now. We will try to use this printf format string vulnerability to leak the stack Canary as well as the libc addresses. And when we leak those libc addresses, we will try to compute the base address from those libc addresses. Remember, we are not going to get the base address directly from the stack. We will still have to compute that by using some addresses. So let's try to use this vulnerable binary to achieve that. As I said, it's going to be slightly complicated, so pay full attention, and if you don't understand something like how I'm doing a specific step, please ask me, because since we are running short of time, I may skip some of the steps, but feel free to ask me if you don't understand a specific step, so I'll be explaining them to you in detail. So the first thing, we will have to interact with the program. If it is a network program, we can basically exploit the format string vulnerability using one packet or one request and wait for the response and then send another request for exploiting buffer overflow. But this is a very simple CTF style binary, right? So it's pretty hard to interact with this binary as one process, because it's just one process. It just takes some input and it just exits. So to be able to interact with this kind of CTF style binaries, we can use something called pawn tools. So I have already installed pawn tools in your VM. So you can basically use that pawn tools. You can basically use this pawn tools to interact with this binary and write this exploit. So where is my full bypass? Okay, let's navigate to full bypass. I think I have copied the vulnerable program into a different location. Looks like that. Yes. So I think I'll have to copy it once again. Let me get that into the current directory. Yep. So this is the program we want there. It will take another 45 minutes. So I'm just setting the expectation in case if you are in rush. All right, so printf and gets, everything is set. Let's remove the binary and let's compile it once again. Let me quickly check if our make-file is properly there. Yes, it is. So yep, so we are all set. Now let's start exploiting this function, exploiting this particular binary. So the first thing, as I mentioned, we are going to use stack Canary bypass, right? So if you see this vulnerable binary, we can basically pass some test input and we can exit from there. And this test input is going to be printed using the printf function, which is vulnerable to format string vulnerabilities. And the next one is gets function, which is taking the input from you. So you can use this gets function to basically provide a long input, which is going to cause the buffer overflow. Okay, so that's the process of using this vulnerable binary. Now, if you provide even longer input here, the ACE, it's going to cause a segmentation fault. But even before that, the stack smashing detection is going to be done. Now, let's quickly check how the stack smashing detection is being performed. I'm opening gdb-q vulnerable. I'm basically loading the vulnerable binary in GDB, and I'll quickly explain how stack smashing is being detected. I'm disassembling the vuln function using disass vuln function. And if you notice, there is, look at this, there is an instruction at this address which is at move vuln function plus 22. There is something from fs0x28 being loaded into RAX register. And if you further go down, some checks are being done with the RAX register, and there is a function stack check fail being called. So basically it is putting some, the program is basically storing some value from somewhere into RAX register, and once that is done, it is just doing its job, and before it is returning to the caller, it is performing some verification here. If you notice on the same RAX register, basically it is taking the, it is getting the same value into RAX register. It is basically taking the same value from the previously shown location, which is here, and it is performing a XOR on the content of RAX register. If it is 0, that means the value that is placed in RAX earlier is not modified. That means there is no buffer overflow. If this value in RAX and if this value are not matching, that means there is a stack based buffer overflow attempt, and it will basically show this message stack smashing detected. So that's how this stack canary works. It's being placed just before the return address. So if this value is overwritten, that means the return address is also overwritten. So that's how it detects stack smashing. Now, how do we bypass this? If you can somehow leak the value that is being placed in this RAX register, which is basically being used to detect the stack smashing, we can basically adjust our buffer by sending this value when we are exploiting the buffer overflow. So just to give a representation here, just to give a better picture, it is checking, so we are just passing some value here, like some A's, and somewhere here it expects a canary, and here it expects probably, let's say, the return address. So this is the original, when you're not exploiting, this is what is expected. And let's say we are passing some more buffer here. This is the original binary, but when you're exploiting the binary, basically you're overwriting this canary with some value. So it's trying to find out the canary value, but it is not able to find out. So it's basically returning a stack smashing detection error. So how do you exploit this? How do you bypass this problem? We will have to use some other vulnerability like format string vulnerability to leak this canary somehow. So we will obtain this canary using a format string vulnerability, and we will place this canary using the buffer overflow vulnerability here. So when the program checks for canary detection, the canary protection, the stack smashing attacks, it's going to fail because we are actually placing the required canary value there. So it has no way it can detect the buffer overflow. So that's the first step that we are going to do. We will have to somehow find out the canary value, and we will have to adjust our buffer in a way that the canary value is available in our buffer, right? So that's the first step, and let's see how we can do that. Is it clear? Any confusion here? Yes, most of the cases, yes, because canary is a random value. It's pretty hard to brute force it. If it is 32-bit systems, you can brute force the canaries, but in 64-bit systems, it's pretty hard because there are also multiple types of canary values. The one that we are dealing with is a random canary, and moreover, it's a 64-bit canary value. So yeah, we will have to somehow leak it using some other vulnerability. Okay, so Yeah, so let's proceed further. So I'll probably just start writing the exploit template because we have less time. So I'm just going to use pawn template. I'm just trying to find out the command. Okay, let me first show you some other things. I'll show you first how to use the format string vulnerability to leak the canary, and after that I'll start creating the template. So let's use gdb vulnerable -q and set up and probably we can just run the binary. If you notice, I'm running the binary using some values here. Percentile LLX. X is to basically leak the hex values from the stack. So percentile X can be used if you are using a 32-bit machine, but since we are on a 64-bit machine, I'm using LLX, long hex values. Okay, so let's use percentile LLX. I'll probably copy it because I'm just going to use a long value here. I'll copy it from somewhere else and let's paste it here. So I'll use this long value as the argument to the program, and I'm running the binary. If you notice, it has leaked some values from the stack. Now at this point of time, this is Greek and German for us. These are some hex values, but they are going to be very useful for us at a later point of time. Now the first thing, any guesses just by looking at these values? Can anybody guess which one could be the stack canary? I'll give 1 minute to think. So basically this output, which is leaked from the stack, has canary values. Just in case if you are wondering what format string vulnerabilities are, how they work and all that, I have recently published very detailed format string exploitation articles. Probably after the training you can go through them. You will have very detailed understanding of format string vulnerabilities. If you see how print functions work, how format specifiers work, and how you can simply exploit format string vulnerabilities, and how you can leak the canaries and all that, with very detailed explanation. So you can just go through this blog later. Okay, for now, yeah, any answers? Which one could be the format string? Which one could be the stack canary? Someone, Sachin Grover, says the one which is starting with F0B5FF. F0B5FF. Oh no, Sachin, it's not. Okay, I'll tell you the answer. The one which is here. Obviously, I'm just starting the binary along with you. I don't have this value anywhere documented, but looking at this is the stack canary, because if you see, it's ending with a 00, which is null byte. So these people who implemented stack canaries are very smart. Even if you manage to put your canary here, if you notice, the canary is ending with this null byte. So that means your buffer will terminate here. So that's another reason why I'm using gets vulnerable function here for the buffer overflow vulnerability. But there will be some canaries which will have a new line also in the canary value. So that means even gets function will not be, even gets function also will terminate the buffer when the moment it finds the canary in the buffer. So I hope you're understanding. You are passing the buffer and you somehow manage to find the canary, but the canary has a null byte. So what that means is, even if you manage to leak the canary, you can't make use of it, especially if you're using a binary with vulnerable function like strcpy, because the moment it encounters the null byte in the canary, it is going to stop copying the buffer. So you can't basically overwrite Rbp and you can't execute shellcode or anything. So that's how canaries work. In this case, we are using gets function, so null byte is not a problem. So now this is the canary. So we have used multiple LLX, %LLX strings here. So that's how and these are the format specifiers. Since we have control on the printf function, we are basically able to pass the format specifiers since it has a vulnerable implementation. And by passing those format specifiers, we are able to leak some addresses from the stack, and out of which one of these addresses is stack canaries. So this is a stack canary. I'm just copying this. Actually, it's not needed because the moment you run the program once again, the canary is going to change. So there is no point copying it, but just saying this is the canary. Now, we don't want to leak all of these addresses, right? We just need the canary to bypass stack canary protection. However, these addresses, some of the other addresses are required for us for actually bypassing ASLR and NX. So let's see what we can do next to basically bypass NX and ASLR. Give me a moment. I'm just making sure that we are doing everything properly. Okay, so to there seems to be a question here. As I said, it's going to just leak the hex values in hex format. The %LLX is long hex. If you have seen format string vulnerabilities in 32-bit systems, you typically see %X or %S, right? So since it's a 64-bit machine, if you just use %X, let's say, you can't get these long values. So to be able to get these longer values, let me show you. So this is the vulnerable program, and we are able to leak like this. Let's assume that we are just using vulnerable and %X, 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 or let me just use some separators. So it's this %LLX is leaking some values from the stack because by using the format string vulnerability. If you notice, if you don't use %LLX, it's only printing as shorter values because it can't give us 64-bit values, because that's the reason why we are using LLX. So when you're dealing with 64-bit machines, you will have to use %LLX. Okay. Similarly, you can use %S to leak some strings that are being pointed by the address on the stack. So that's format string vulnerabilities. I know I should have covered more details about the basics of format string vulnerabilities, but we don't have enough time. So just go through the articles that I have just referred. Okay. So yeah, so that's the first step. We managed to leak the stack canary. If you notice, we have stack canary here. Now, to be able to get the actual canary value by using the exploit, we can count it actually 1, 2, 3. I mean, what is the number at which we can actually get this value? For instance, 1. This is the first value. This is the second value. This is the third value. Similarly, I think this is the 41st value. If you count all of these, I think it becomes 41. Let's quickly try. /vulnerable %41 LLX. Let's try it again. I think it's 41 LLX. Oh, sorry. I think we need to use a dollar here. Yeah. So if you notice, let me just show it again. So this is the stack canary in this run. Now, if you run like this, basically the dollar has to be escaped. So I just added a slash here. And so basically, if you want to extract a specific entry, if you say this is the 41st entry, this is the way to extract that. Instead of extracting all the entries from the stack based on how many number of percentile LLX you have passed, you can just pass the number at which you want to extract. So if you see, we are only getting the canary now. So that's how we can use it in the exploit. So that's the first one. So I'm just going to use pawn tools to basically produce a template so we can directly use all of these things in the exploit. I'm just typing pawn. I think let me just find out the command. Template, and the vulnerable program is this, and I think we can write it into exploit.pl. Let's open it up. Yep. So I'm just going to use pawn tools as I mentioned earlier. So using pawn tools, I have created a template here. Pawn tools is basically a CTF framework which can be used to interact with the binaries which we can use it to interact with the binary. So now this is the template which is created, exploit.pl. Let me quickly open that. By default, it creates with Python 3. It has a large amount of text. Don't get confused. Just follow what I'm doing. First step, I will change this to Python 3. That's done. Next step, we want to pass the command line arguments to this program, right? So that can be done here. Return process exe path is there, right? So basically it is going to call the function process using which the process will be started, and then we want to pass some arguments to that. So the way we can pass arguments is exe path, comma, and we can basically specify percentile, the same $41 LLX. So this is basically going to leak the stack canary for us by using this exploit. This is, don't get confused if you are using pawn tools, if you're seeing pawn tools for the first time. If you remember earlier, we were writing some simple Perl templates, right? It's basically the same thing. Instead, we are using pawn tools to automatically generate it because we need to be able to interact with the program at runtime. So I'm using this percentile $41 LLX. That's pretty much it. And if you go, that will basically leak the address for us. And here, exploit goes here. So this is where you're going to write all your the complete exploit. So what I'll do is I will just remove all the unnecessary stuff here. All right. So io.start is going to start the binary for us, and once that is done, we can actually read the canary using io.readline. So this is once the binary gets started with the arguments that we are passing using the process function, it is going to leak the canary, right? So that canary is going to be placed in this particular variable called canary. We can actually quickly print it out. So I'm just going to use print canary. So let's save this. chmod +x exploit.pl. We will bypass all of these, but for now we are just dealing with stack canary. If you notice, the stack canary has been leaked. That's fine. So one problem is solved. So we managed to write a simple template script which is leaking the stack canary. Is it clear so far? If yes, we will proceed further to understand how we can leak libc base address and use it to bypass NX and ASLR. So we basically passed one argument which is exactly leaking the base stack canary. So that's pretty much it. Now let's move on to the ASLR and NX part. once again, we are just going to use the same format string vulnerability by using /vulnerable, and we will have to use the same old percentile LLX thing. Just give me a moment, please. I'm just copying some text here so that I can show it to you. Okay, so once again, I'm just executing the binary like this. If you see this, once again, this is where we have the canary value. Now, if you remember, in the return to libc as well as, in the return to libc attack, we were using the base address of libc library, right? So that is something that we need now. Now, to be able to leak the libc address, the base address of libc, to be able to leak the base address of libc, basically we will need to find out some address in this leaked addresses which is coming from the libc library. So the point is, we should be able to find out one address at least in this which is actually coming from the libc library. It doesn't matter which function or what it is. We just need to find out the libc address from these leaked libraries. So from that address, we are going to compute the base address based on some knowledge that we already have. Okay, so let's see how we can do that. So first of all, let me load this in GDB. Vulnerable -q, set up a breakpoint at main, and let's run this binary using this. Okay, so we should have gotten some addresses. I'm just going to copy them. Looks like it did not give us yet. So let's do one thing. Let's probably set up a breakpoint at one function. So by the time we reach there, we will get some leaked addresses. I'm just continuing the execution. Here you go. You got some addresses. I'm just copying them. Now the idea is we want to find out at least one address that's being leaked from libc. So these are the addresses that we have gotten right. Now let's try to find out let's enter some text so that it will continue the execution and the breakpoint is hit on ret instruction. Now let's type vmmap, and if you notice, these are the entries associated with libc. Now identifying libc address from these leaked addresses is as simple as that. Finding out one address from this leaked addresses in this highlighted range. So this is the range for the libc addresses, right? So this is where the libc library is being loaded. Now if you can find out at least one address from these leaked addresses within this range, then that's basically the libc base address. That's basically one address from libc. So let's see if we can find out any such addresses in these leaked ones. If you notice this, this is one good candidate that we can check. 7ff ending with B6FC8, starting with 7FFFF. If you notice, all these addresses are starting with 7FFFF. So basically we already found one. So all of these addresses are on the same range, right? So this address possibly belongs to libc. So if you remember, this is the 41st value. So this becomes 40th value. So from so far the knowledge we have is 40th value is actually you can verify this within the vmmap. It's basically within that range. So the 40th value is from libc and 41st value is from is the stack canary, is the canary. So we have gotten this information so far, but this address that we are getting is an absolute address. What we want is the base address, right? So to compute the base address, any ideas? Anybody has any ideas? How can we compute the base address? How can we compute the base address at runtime? Any ideas from anyone? Okay, let me explain. Now we know that this is the base address of libc in this case, right? So I'll copy this. But this base address will obviously change next time when the binary gets started. Obviously, in GDB, ASLR is disabled by default. So if you check this address, if you check the base address of libc within GDB, you will see the same address every time. But when you check these addresses outside GDB, they will change every time. By default, GDB disables ASLR. You can enable it if you want. The command is ASLR space on. Simple. Okay, so this is the address that we have gotten, and at this point of time, this is the base address. What happens if you subtract the base address that we currently have in GDB from this? We will get some offset, right? So we know this value and we know this value, and these offsets will always stay at the same relative address. If you remember, we were using bin.sh offset within libc. We were using system functions offset. We were using mprotect functions offset. All of these addresses, all of these offsets will always stay at the same place. So offsets will never change. Only the base addresses will change. So if you know any two addresses, you can calculate the third one, right? If you know any two values, you can calculate the third value. In this case, we know one absolute address, we know the base address, and we want the offset of this address. Let's calculate that. I'll just using, basically you can use calculator, but in this case, I think I'll just, let me use calculator just to avoid any confusion in case if you have. So I'll use hex mode. I'll paste it here, minus the base address that we have gotten. So let's paste it here, equals 1F0FC8. So 1F0FC8. What did I just mention? This offset will always be constant. This means if you can somehow leak this address at runtime, which is the 40th value always, and you know the offset, you can obviously calculate the base address, right? How do you calculate that? You just need to subtract this offset from the leaked address and you will get the base address. That's it. So just use these calculations and just reconstruct the exploit once again. That's simple. So let's do it. So let's do that. I'm just going to remember this is the 40th value, because if you notice here, this is 41st value Canary, and this value is just before that, so it should be 40th value. So within our GDB exploit, within our what is that, the template that we have used, we can just update that. It will take another 15 minutes. We will wrap it up. Okay, so let's open up exploit.pl. Oh, it's saved as PL. That's my bad. It should be Python, obviously. Though the extension doesn't matter. Let's make it Py. So exploit.py. I'm surprised nobody pointed it out. Okay, so we are already leaking the stack canary here. Now we also want to leak the libc address, right? So let's do that. I'm just going to add one more entry here, percentile 40 $lx or LLX, and I'll separate these two with a semicolon, a colon. Okay, so that should give us the libc address first and then stack canary next. Let's simply execute it first and see how it looks like. Exploit.py. Look at that. It is leaking two addresses. This is the this one is going to be the libc address and this one is going to be the canary. That's it. We can now construct the buffer by properly extracting these values and calculating everything. Now I will quickly do this. So we have everything done. Since we have less amount of time, I'll probably copy from what I have already written earlier. So I'll just go to backup and I'll go to full bypass and I'll go to exploit or final.py. So this is the file. I'll just copy line by line so you will understand why I'm doing and what I'm doing. We are pretty much done. So this line we have already written. Okay, I think I'll just use this one because it contains some good strings being printed when you complete the exploit. Okay, so the first thing, I'm also placing the shell code that we are going to use later. The concept is all done. I mean, that's the whole concept. We are just going to manually write everything now. So instead of typing everything, I'll just copy and paste. So the first thing, we have a variable called shellcode, which contains the shellcode. All right, and then let me just close everything else just to avoid confusion. And after that, we are leaking the whole libc address as well as the stack canary. That part is already done. If you see this, this part is done, but let me just paste it from there so that we will have proper variable names. After that, we are just printing the leaked addresses, which we have already done earlier. Now let me just execute it till now. Exploit.py. If you see, we are just leaking what we have leaked earlier, so that part is already done. Now let's continue with the exploit. Now we need to extract these two values programmatically, right? So let's do that. First, I will extract the first. So if you notice, I'm just extracting the first 12 bytes and I'm just converting it into an integer value of base 16 so that we'll get proper hex values that can be used as addresses, right? And using that, we are calculating the libc base. How are we calculating the libc base? If you remember, we got an offset earlier, and whatever the value that we are getting from the leak, we are taking that and we are just subtracting the offset that we have computed earlier, which is this 1F0FC8, 1F0FC8. So this should give us the libc base address, right? Once this is done, we can actually print it. I'll show you. I'll just print it now. So here it is. If you run this, it should print the computed base address, libc base address. So this is what we were hard coding earlier. Now if you run this, look at that. It has leaked this address from the stack, and using that, it has computed the base address of libc. Right, now let's move on to the next step. So what else? We have libc base address. So we can basically start using return to libc attack that we have seen earlier, and when we overwrite the canary, we will just have to place this canary value that we are extracting, the second part of the leaked address, right? So the next step is basically to construct the return to libc attack. So I'm just making use of this. We have already discussed how to construct this return to libc payload. So I'm just copying it. Basically, I copied it from the previous exploit into this. If you see, we have a ret instruction here, which is to prevent the stack alignment issues, and we have pop RDI bin sh address. It's the same exploit that we have written earlier. I just added exit address at the end, which I asked you to do as homework. Now the return to libc exploit is finished. So what can you do with the return to libc exploit? We can bypass nx, right? So nx can be bypassed so that we can execute bin sh shell using system function by using this part. So nx part is done. We already did this earlier, so we are just reusing that. Now to bypass ASLR, we leaked the libc base. We leaked some libc address and computed the libc base, right? So with that, ASLR is also bypassed because we are calculating it at runtime. Now the last and final part, when we send this payload to the target binary, we will have to properly adjust the payload in a way that it contains the canary value as well. So let's compute the canary value from the leaked address. So to compute the canary value, I'm just let me show you what I'm doing here. It's basically programmatically extracting the values that are leaked. So I'll just try to run this for you. Exploit.py. Look at this. So we have gotten these values from the leak, and computing the canary value is simply basically extracting the second part, which is this. That's it. It's nothing. It's not rocket science. We are just extracting it, and that's the canary. Now we will have to use that in our exploit. Okay, so let's go back, and now let's craft the complete exploit. I will first use 264. Oh, by the way, I missed one thing. I missed to show you one important part when showing you the canary leak. So here you also need to find out the offset to canary. Once again, you can basically use the same technique. You can overwrite the canary value with some pattern, and then you can find out what is the offset to leak, override the canaries. So here I'm just removing all of these extra pasted ones. I'm not sure why, but they are being pasted multiple times. So here the canary part is done earlier. Now we are crafting the actual payload, the 300 byte payload. First we are placing the shellcode in the beginning, and we are passing some A's minus the length of the shellcode, right? Pretty clear till here. And once that is done, we have to place the stack canary. So in pawn tools, we can use, just like your pack function in Perl, we can use this P64 of the exact hex value so that it will be converted into Little Endian format for you. So that's the P64 function here within this. That's the P64 function here within this template. So we have leaked the canary earlier, if you remember this one. So this, just in case if you are unsure, this leaked of 13:29 is extracting the canary part from the leaked address, which is the 13th character to 29th character. That's it. And we are converting it into an integer. Once that is done, we have placed the canary. This is the offset to canary value, which is here. And once that is done, pretty much everything is straightforward. We will just have to place the remaining exploit with the Rbp and Ip register. So after the canary, we will overwrite Rbp. So this is going to be the structure. First, we will have long buffer. We will have canary. If you don't want to find out the offset to canary by using the, if you don't want to find out the canary by using the pattern, you can basically use the RBP offset -8, because this is going to be the structure. Canary will be here, RBP will be here, and RIP will be here. So since we already know the offset to RBP, we can just make it -8, and that will be the offset to Canary. Okay, that's what we have seen. That's what we are going to do now. If you see this, 264 minus length of the shellcode, and we are going to use the Canary next, 8 Bs. I think I'm wrong. It should be, yeah, I think it's right. So these 8 Bs are for the RBP register, and then the next one is the RIP. So from here, RIP will be overwritten, and the return to libc payload can be executed here. So it's just the return to libc payload. We are just constructing using Python. If you see this is the return to libc payload from here to here, and this is RBP, this is Canary, and this is the junk. Once that is done, we are sending the payload to the binary by using io.sendLine. So this is going to send the input to the gets function, right? So that's basically payload that we have constructed so far. If you just save this file, let me quickly show it once again, the exploit part. First, we are starting the binary, and then we are actually the shellcode is not needed. I have anyway we are using return to libc, so basically it's not needed. So that's a mistake. I have added it here. Now the leaked address, the leaked variable contains both the libc address as well as stack canary. Once that is done, we are calculating the libc base by subtracting the offset that we computed earlier manually, and after that we are using this libc base to actually construct our return to libc payload. After that, we have extracted the canary, and finally we have just adjusted the buffer with the canary and the payload. So let's run this. .py. Hopefully everything should work. If everything works, we should have a shell. There it is. So this is how we can basically bypass canaries, NX and ASLR by chaining multiple vulnerabilities. So if you see any real world vulnerabilities these days, typically they'll have to deal with all of these modern exploit exploit protections. So if you see, we are using a Ubuntu 2004, it's a modern machine, and for this specific exploit we have enabled all the protections. As you can see here, NX enabled, Canary is found, full railrow, and ASLR is also enabled. Let me put on my earphones. If you have any questions, feel free to ask me. If not, I think that's the last topic that I wanted to cover.